Ladies and gentlemen, on behalf of the organizing committee, we would like to welcome all of you to the 6th EAI International Conference on Industrial Network and Intelligent System, INISCOM 2020. We are delighted that the conference aims to providing a premium forum for presentation of research results and experience reporting on the cutting-edge research in computing, telecommunications technologies, and application of 5G IoT, AI, and cybersecurity for the fourth industrial revolution. This year, we received 59 submissions from about 200 authors and co-authors of 12 countries. Each paper receives at least 3 peer technical reviews comprised of more than 30 TPC members from academies, government laboratories, and industries. After carefully examining all the received review reports, the INISCOM 2020 TPC finally selected only very high quality paper, including 26 papers for the presentation and at the conference and publication in the proceedings. This year, due to the COVID-19 epidemic, INISCOM 2020 will be held in a live online setting to accommodate the current restrictions. The conference will feature one keynote speech from renowned world-class leader in the area. From Kumo National Institute of Technologies, Korea, will give a talk on reliability of industrial Internet of Things. The technical session of INISCOM 2020 reflects the growing interest in telecommunications system and network, industrial network and intelligent systems, hardware, software, and application design, information processing and data analysis, and security and privacy for the fourth industrial revolution. Outstanding paper will be selected and invited for the special issues in well-known international journals such as ACM Springer Mobile Networks and Applications, MONET, and EAI endorsed Transaction on Industrial Networks and Intelligent Systems. A conference of this size cannot be organized without the hard work and dedication of many people. We would like to thank all authors who submitted their manuscript, as well as the chair, co-chairs, TPC members, invited reviewers for their contribution to the conference. Special gratitude goes to the Springer for their technical sponsorship. We would like to recognize our organizer and financial sponsors, Liquidon Technical University and Witten University in Vietnam, the European Alliance for Innovation, Newton Fund, Institutional Link, through the Flyby Flood Monitoring Project delivered by British Councils. We hope all of you enjoy the INISCOM 2020 technical program and find this conference a productive opportunity to explore, exchange ideas, and best of all, come back next year to contribute to the INISCOM conferences. Thank you very much.
Ladies and gentlemen, let me welcome you to the 6th EAI International Conference on Industrial Networks and Intelligent Systems, EAI INISCOM 2020. I'm Natasha Onofrey, the conference manager of this year's edition. Unfortunately, due to the coronavirus pandemic, I'm not able to greet you all in person right now. So I'm using this opportunity to address the organizing committee, the authors, and our online audience on behalf of the European Alliance for Innovation. First of all, I would like to thank all of you for being a part of this conference and for your involvement with EAI. Above all, I would like to express my gratitude to the General Chair Huang Fang-puk and Program Chairs Trung Kyu Dong and Nguyen Son Vo for their excellent work in organizing a successful event in these difficult times. During this streaming, you can actively participate in two ways. Firstly, you can take part in the Q&A discussion in Slack by following the link below this video. Upon accessing the INISCOM workspace, you will be able to enter all the channels, which are divided by sessions. Secondly, you can vote on individual presentations and leave your fellow researchers feedback on their work through our tool, EAI Compass. In a few minutes, we will explain how to access the EAI Compass and how to leave and receive feedback for presentations in this conference. As you know, EAI INISCOM is an annual conference, and I'm glad to announce you that in April 2021, INISCOM will take place in Hanoi, Vietnam. I invite all of you to participate in our 2021 edition by submitting your papers, by organizing a workshop, or by joining the Technical Program Committee. In fact, at EAI, we're constantly searching to promote innovative research in the field of information and communication technologies. So if you have an idea for a workshop or a conference, or you would like to collaborate with us in any other way, please contact me at the email below this video. After my presentation, my colleague Michael will tell you more about the EAI entity, the tools we provide, and the aforementioned voting process, which you can already use during this conference. Thank you all for your attention, and I hope to welcome you all again next year in Hanoi. And now, enjoy INISCOM 2020.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work in progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hello everyone, it's my honor to present my talk at INISCOM 2020. First of all, I appreciate to all committee members and staff for this successful INISCOM 2020 in spite of COVID-19 pandemic virus. Today, my talk is concerned to reliability and real-time issues in industrial IoT. I hope this talk helpful to understand the state-of-art issues in the area of industrial IoT. Nowadays, with 5G technologies, ultra communication and ultra intelligence systems enable to smart factory and smart city and smart logistics. In particular, cyber physical system with AI and ultra reliable low latency communications, one of the 5G industrial standard, enable to innovative transformation of the industrial field. In view of practical concern, this transformation will continue with new technology. By through this graph, we can observe numerous IoT devices increasing dramatically, especially IoT using 5G and 5G beyond technology will be adapted for industrial area in explosive way. Okay, in this one of the example of the smart factory using the 5G AR glass to control and monitoring the system. Also 5G connected car for logistics. And the other one is kind of the example of the LG U Plus, one of the telecommunication company at Korea. They designed some kind of autonomous robot with many smart IoT technology to enable the innovative and futuristic smart factory. In this slide, I want to talk about industrial IoT technologies. The IoT is start from IoD. IoD stands for Internet of Device. Is kind of sort of the route to route communication. And next version of the IoD is kind of communication between person to person. We call it as the Internet of Person. The starting era of the web browsing, we call it as IoT. Nowadays, this kind of technology becomes IoT, machine to machine. It's composed of the things such as sensors, actuator, controller, and also infrastructure such as communications, 5G, enhanced URLLC, switched Ethernet. And for optimizing the system, the AI, big data is combined with this kind of infrastructures. Nowadays, we can see some kind of futuristic cyber-physical system. In this slide, I want to talk about some kind of issue of the reliability issues for industrial IoT. Usually, the many scholars can consider the FOPAD. The reliability can be considered as a FOPAD from error correction to communication and networking. In the case of error corrections, we can consider reliability for transmitted data packets using FEC, ARIQ, also designed lightweight MAC protocol to consider requirement of the factory environment. And for data handling, we have to consider some kind of the huge volume of data from IoT, industrial IoT. It might be via big data. We have to extract useful data for control, monitoring the device. So therefore, the data analysis solution from the edge device are necessary. In the case of middleware, so it's kind of one of the common platforms. The reliability at service level of the IoT depends on some middleware, such as MOM and DDS. So the open issue at middleware is to use some existing real-time middleware to combine industrial IoT technology. In the case of communication and networking, there is many standards previously, but nowadays, enhanced URLLC release 13 might be used for the standard for industrial area such as smart factory. Now we will try to talk about using example regarding the reliability of the industrial IoT. You can see one of the examples, automotive vehicle. What happened there? What kind of the issues? Usually the automotive vehicle, automatic vehicles, some fault at issue by the noise. Can you see some kind of vibration or temperature? It's caused some kind of the errors. The bit flip 0 to 1. It caused some kind of corrupt the thread, and also through the digital logic, it caused kill thread might be called some kind of open throat valve. It's a kind of the diagnosis of the vehicle. So to prevent this kind of phenomena, we can consider many kind of approaches. One of the approaches is kind of the deep learning technique, and also the redundancy, some kind of pattern. The redundancy-based patterns may be considered to prevent this kind of the malfunction and the failure. In this slide, we try to investigate reliability issue through the hierarchical structure. Actually, as a matter of fact, IIoT is different with IoTs because it considers harsh environments such as factory and power delivery, military logistic, very noisy environment. Also, we have to consider the large volume of data from IoT device. This data traffic may be categorized the various the type of the data, periodic, sporadic, unperiodic data. And also, some kind of, because industrial IoT have to consider the time-sensitive application, mission-critical system. It have to consider some kind of deadline, so the scheduling for deliver the packet within time. So for this industrial IoTs, we have to consider some low latency, short delay bound network, and also consider some kind of fault tolerant network. And so for this one, we also try to consider some kind of the edge computing is one of the part of the clouding computing. So how can we optimize, connect the edge computing to fog and clouding computing? So in view of the clouding computing, at this slide we try to check how can realize reliable fog and edge computing. Normally we can categorize the things layer, edge layer, and fog layer, and the distributed cloud layer in the case of the factory system. So usually it's some kind of the between edge layer and fog layer, the real time and write task, and also security have to guarantee for data transmission. In between the fog and the cloud layer, it's a more heavy task, less time sensitive data will be delivered. So considering this hierarchical architecture, we have to consider some kind of sort of network overhead, and how can optimize network size, and also reduce node failure is kind of the challenging issue in the case of industrial IoT with edge computing. As an example, there is a kind of example connect between the edge computing and clouding computing. We call it as IoT-MT, Internet of Military Technology, and IoT-BT, Internet of Battlefield Technology. So you can find as a decision and command layers that may be connected from battlefield through the clouding computing for field operation and control and central command. So in the case of battlefield, the soldier have many multiple sensors and wearable device, and also some weapon system. They also have an embedded system or some kind of control system. Also vehicles, some equipment also have some kind of common thing. Embedded computing, some kind of networking is common thing. Maybe it's a closed 5G, closed LTE might be used for this kind of system through the edge computing. Another issue, industrial IoT, is we can call it industrial IoT meet AI. So as you know, there is a massive amount of data generated from smart factory asset. So it might be via the big data from the sensors and the controller, actuator. So this big data have to store it, and also we have to find out some useful data from this big data. For this one, industrial AI and some machine learning enabled to find out some kind of useful data. Through it, accelerating time and reduce cost for smart decision making. So through this one, in feedback and recommendation, decision making for management and control, all procedures will be enhanced. So it shows some interaction between three major components in industrial IoT. Industrial IoT is, as you know, some needs ultra high reliability because it have to charge it on the industrial section, always on, and it's extremely low latency to control the actuator and some critical system. In the case of reliability perspective, we can consider some kind of the several issues. So one of them, we have to consider some kind of the fault detections, abnormality detections during the operation time. Also find out some kind of the hackings and DDoS attack. Some kind of is very critical thing. So try to imagine some kind of pureness inside the factory controlled by the hacker. It's very critical issue. So we have to design the system, consider reliability, to considering fault detection using AI and some kind of the detecting the attacks from outside is one of the issue. And also real-time issues. We can consider some kind of the basic things, but industrial IoT is as like some kind of industrial control system, the mission critical system. They have to support low latencies, short delivery time. So for this one, we have to consider some kind of network infrastructure such as fog computing, cloud computing. So how can reduce time? This kind of the connecting time is kind of the open issue. More advanced items of the industrial IoT can be combined with deep learning, also some kind of the using the big data, and also deep learning maybe can focus on some kind of the high speed and high accuracy in industrial domain. In particular, as some kind of between clouding layer and edge layer, some kind of we can combine some kind of deep learning to optimize the collaborations between each layer. And next, I will introduce some kind of the new industrial Internet of Things. We call it a physical Internet paradigm. The physical Internet paradigm is developed towards a global means for industrial logistics and transportation, which requires a global reach of feasibility and monitoring. Although IoT technology can serve as an enabler to achieve the goal of physical internet, designing the IoT ecosystem is still facing several challenges. Among them, obtaining reliable communication and operation is the key objective to synchronize the material and information flow in the physical internet network through the smart object, smart network, and smart management system. Enabled in IoT, the advanced technology, innovative service can be developed to support effectively the logistic activity in physical internet, thus improving the operation efficiency. The dynamic nature of the logistic activities requires a high reliability of services for enabling the real-time provision with high quality of service even from remote providing centers. Such demand directly linked to reliability of communication system, data computing algorithm, and even embedded hardware and software. So today, I introduce some issue of the industrial IoT in view of the reliability and real time. So in the case of reliability issues, we can categorize from application to perception, application and middleware and network perception. So in the case of application, we have to consider usability. In middleware, so we can have to consider dependability. In the case of network, we might be consider availability, and perception combined with the AI, we can consider maintainability. And real-time issues in industrial IoT is still ongoing. Enhanced UR LLC, one of the standard industrial standard of the 5G, might be settled down soon. Industrial smart factory and edge computing to reduce latency and the fast data processing is one of the key factor at the industrial IoT. And for security industrial IoTs, some kind of lightweight blockchain technology might be necessary in near future. Today, I talk about some kind of the overall issue of the reliability in real time. If you have any kind of question and comment, please feel free to comment directly to me or send email. Thank you for your attention. I hope see you again.
Hello, my name is Rashid and my advisor is Berk. I am studying computer engineering and we are participating here from Istanbul Technical University, Turkey. I am going to present the paper Intelligent Channel Utilization Discovery in Drone-to-Drone Networks for Smart Cities. Firstly, I am going to introduce to you our subject with motivations and challenges followed by our contributions. Next, I will explain our network architecture and system model. I will end the presentation with the performance evaluation and conclusion of our work. Let's start with the introduction. It is known that smart cities enhance life quality with intelligent things, and drones are a crucial part of them. With new smart city technologies, drones are rapidly developing and becoming extremely useful in a variety of areas from civil applications to military missions due to the structural advantages and moving flexibility on air. Surveillance, search and rescue missions, delivery of goods, construction, and natural disaster monitoring are most standing out applications of drones. The achievement of these applications depends on improvements in network performance. In this aspect, to provide reliable, efficient, and stable drone-to-drone networks, monitoring resources of aerial system is a crucial mission because that minimizes the cost of the maintenance of data flow. Thus, we focus on the topic of resource monitoring, which is channel utilization for the drone-to-drone networks in smart cities. There are several provided solutions for resource monitoring for both physical and MEC layers. Physical layer solutions are not accurate, effective, and reliable because the physical layer can be affected by other signals or signals cannot reach the destination due to the shadowing effect and mobility of drones. When we examine the MEC layer solutions, they have a high time complexity. Let's look at our contributions. Firstly, we propose a new system model consists of searching and finding sublayer and functional sublayer modules. This model works on the MEC layer of IEEE 802.11 RTS protocol. Secondly, we introduce a practical and more straightforward channel utilization calculation using the properties of the IEEE 802.11 RTS protocol. Finally, we present a novel monitoring approach with a K-means clustering algorithm to visualize and analyze network traffic in the Voronoi diagram in a more practical and faster way. Here, our network architecture. The network topology of our model consists of N drones with a one searching drone, as in figure 1. These drones are communicating with the IEEE 802.11 wireless networking protocol with the RTS-CTS mechanism. The RTS-CTS mechanism is created for avoiding the hidden terminal problem in wireless networks and allows only one pair to communicate in the channel. Drones can fly at different heights with a specific moving pattern. However, the searching drone always flies at the predetermined altitude. All drones repeat their flying patterns after reaching destination coordinates. Also, drones communicate directly with each other on the same channel without authentication messages. Moreover, the channel is always occupied and the frame size is randomly generated in the network. Let's continue with the system model. We divide the proposed system model into two coherent sublayers named searching and finding sublayer and functional sublayer. Searching and finding sublayer has two modules named sensing and data classification. Furthermore, the functional sublayer has two modules named calculation and visualization as in the figure 2. The details are explained in the following slides. Searching and finding sublayer includes sensing and data classification modules. Our first module is the sensing module. It handles the movement pattern of the searching drone and operations of collecting data from the channel with sensing. This information contains coordinates of the communication drones, source and destination address of the frame, duration ID in the frame to keep nav timer, and frame types such as RTS-CTS data or egg. After the sensing channel for gathering this information, this module transfers collected data to the next layer called the data classification. And the second module is that data classification. The transferred data from sensing module is classified here to match the data with the drone data sections. The coming information from the below layer is assigned to the drone data if there exists. In the case of a new drone whose information does not exist in the drone data section is discovered, then the new part is created in the data classification module. All other information about this drone will be assigned this section in the future data gathering. This module's main aim is grouping collected data with corresponding drones to make it easier for calculations in the future. After all these operations, the classified data is transferred to the up layer named calculation module. And here the second part of our system model. The functional sublayer includes calculation and visualizations modules. Calculation module is a crucial part of our model. This module contains submodules called channel utilization and traffic type. Channel utilization module is responsible for computing the channel utilization of the area. To do that, this module uses the properties of the IEEE 802.11 RTS-CTS protocol. Due to this protocol, only one pair can communicate at a certain time. Other drones should wait until the null vector reaches 0. After that, if they win backup timer before the other drones, then they can transmit their data as in the figure 3. And figure 4 shows the sample scenario. This scenario is an example of our model with less number of drones with the searching drone. The communication sequence diagram of the area can be seen in the below part of the figure 4. In our model, we concentrate on the repeated cycle of RTS-CTS mechanism denoted as T-slot time. It can be understood that T-slot time can be calculated focusing on the starting time with the RTS frame after the backup timer until the egg frame is transferred, which shown in the figure 4b. In this interval, only one drone pair can transmit, and the total transmission time for the data always has same subtime intervals except for the data frame size. Other time intervals like diff's duration are constant values determined by the protocol. Hence T-slot time can be denoted as in the equation 1, where components of the T-slot time are constant values which depend on the standard of the protocol except T data. The T data can be changed according to the frame size. In this time interval, due to the data frame size show us the real traffic in the channel, we focus on the T data to calculate channel utilization of the area. Other values are minimal and constant. Hence, the rate of the T data and T-slot time give us a channel usage in the time interval T-slot time as in the equation 2. In our model, there is no idle time interval between each T-slot time. Hence, total utilization can be expressed as a summation of the rate using equation 2 as in the equation 3, where n is the total number of repeated cycles T-slot time in the channel. The successful RTS-CTS transmission contains multiple T-slot time intervals successively, as in our model. These intervals are independent, hence average utilization can be calculated taking the average of the equation 3 and as in the equation 4. Equation 4 provides a powerful and simple calculation of channel utilization only sensing once in the time interval of T-slot time. The calculation of the channel utilization can be possible when T data interval is known. Hence, we present a novel approach for determining the T data interval using null vectors. After sensing once the channel, the null vector is created for searching drone, and the average channel utilization using the equation 4 can be calculated with the size of null vectors. Thus, we use 4 types of null vector, and the duration of these vectors can be calculated as in the equation 5 to 8. It can be seen from equation 5 to 8 that all null vector types contain T data interval except navh. In our model, the searching drone can only sense the mentioned frames except navh interval. With all detected null vector types, T data can be determined because all other time intervals are known by the protocol. Hence, in this module, it is possible to calculate the T data interval using our algorithm. We decide which equation we can use according to the received type of the frame. Each frame type has a different calculation equation given as in equation 5 to 8. And using these equations and equation 2 to 4, ninth equation can be derived, where n is the number of sense frame number and T data is calculated using our proposed algorithm. Also, T-slot time is determined according to the sense frame type. Shortly, equation 9 gives us an individual channel utility for each drone. With equation 3 and 4, known T-data interval allows us to calculate average utilization. Hence, knowing the T-data interval provides an accurate calculation of the average channel utilization. Moreover, the second part of the calculation module is a traffic type submodule. This module is responsible for determining the traffic type of the region in the Voronoi diagram. According to the average utilization of the channel traffic, which is calculated in traffic density module, we determine the traffic type of the region in the Voronoi diagram in terms of level, which are low, medium, and high traffic. We define the low level as a percentage of less than 30% and the medium level as a percentage of the between 30% and 60%. Also, we specify the high level as a percentage of the more than 60%. Here, the second part of the functional sublayer, which is the visualization module. After the channel utilization and network type are calculated for each drone, the Voronoi diagram is created and visualized with each drone's coordinates in this module. This diagram contains regions with average channel utilization and network traffic type. In this module, the drone coordinates are grouped, and after that, we construct the Voronoi diagram. The grouping operation is done with the K-means clustering algorithm, which is one of the simplest and popular unsupervised machine learning algorithms. K-means clustering results in a partitioning of the data space into Voronoi cells, which help us to create Voronoi regions in our model. The Voronoi diagram gives us a more precise and discretized visualization of our model. Figure 6 shows the result of our model as a visualization approach. The figure 6 consists of two parts, which first part shows a map before our work as a physical layer, and the second part shows a diagram of using our model. Each section of the figure 6 has a point A on the same location to offer the same place for evaluation channel utility. When we examine figure 6, we can see for point A, it is not reliable to find out channel utilization in the first part of the figure. For some samples, there is no specific channel utilization, or there are multiple values that we should consider all of that. With our model, as in the part B, we can detect channel utilization more reliably and accurately. Furthermore, we show network traffic types in regions which cannot be seen in the first part of the figure. Let's continue with the performance evaluation of our model. We show our results using our simulation written with Python. We show the comparison of the physical layer and our model with different parameters such that average sensing time, power consumption, and used area during calculation in our simulation results. We experiment average sensing time of the searching drone with make layer solution and physical layer method. Figure 7 shows our model decreases the average sensing time about 25%. The reason of that, the physical layer approach, the channel is always sensed, but in make layer solution, the channel is sensed when noise is finished. We also examine power consumption of the searching drone with our simulation. Figure 8 shows the power consumption of the searching drone during the sensing phase, according to the physical layer and our solution. It shows that our model decreases the power consumption by about 26%. The reason of that, the physical layer approach, the searching drone senses channel all the time, but in our make layer solution, the searching drone senses channel when noise is finished. Furthermore, figure 9 shows the used area during calculation phase measured by the searching drone according to the physical layer and our model. It shows that our model decreases the used area during calculation phase about 57%. The reason of that, the physical layer approach, all visited area is considered, but in our make layer solution, due to the RTS-CTS, only one pair can communicate in the area. Let's finish our presentation with the conclusion. In this paper, we propose a novel channel utilization monitoring approach for drone-to-drone networks to evaluate the performance of the wireless link. The searching drone flies in the air with a specific flying pattern and sends the channel to locate other drones. Our protocol-based system model processes all sense information and calculates channel utility with our novel method. This method benefits from IEEE 802.11 RTS-CTS protocol. which allows continuous and discrete communication with one communicating pair at a time in the channel. Shortly, our solution is more reliable, accurate, and practical. Furthermore, we provide novel visualization method with Voronoi diagram. The power and simplicity of the Voronoi diagram are applied, and we create a channel utilization map in our work. We divide the map into Voronoi regions with a k-means clustering algorithm for corresponding heights and show channel utility for each area. Furthermore, we decrease the average sensing time of the channel 25% with our model. We also reduce the power consumption of the searching drone by about 26%, and we fall used area during the calculation phase about 57%. In the future work, this protocol-based approach for monitoring channel utility can be applied on Wi-Fi 6, which is a data-driven protocol as we proposed, and the 3D Voronoi diagram can be created to get more robust examination of the link performance. AI-based evaluation of the channel utility and network traffic type also can be applied to the work. Thank you.
Hello everyone, my name is Phan Thanh Minh. I'm from Ho Chi Minh City University of Transport, Vietnam. On behalf of the research team of co-authors from Duy University, Văn Lang University, Vietnam, and Queen's University, Belfast, UK. Today, I'm here to present to you about downlink resource sharing and multi-tier caching selection maximize multicast video delivery capacity in 5G ultra-density network. My presentation in 6 parts. Firstly, I'm going to look at 1. Instruction. Secondly, I will look at 2. System model, and 3. System formulation. Then I will move on to example for DRS MCF optimization problem and solution. Next, I will focus on 5. Performance evaluation, and finally 6. Conclusion. In the introduction, I will present 3 content. Firstly, problem. Secondly, related work, and finally, solution. I will start with some general information about the rapid increase of mobile user and various video application and service problem. According to Cisco reports 2022, about 79% of mobile data traffic. There are a number of mobile users in close vicinity of each other that have the same interest of video content. Easy context by exploiting the benefits of common interested in sharing nature of NC of mobile user and broadcast nature of wireless medium multicasting techniques play an important role among 5G networks, since they can provide the system-wide a high engine and spectrum efficiency solution and high video delivery capacity. Release work. The multicast techniques has been studied to apply to device-to-device communication with extent of the mobile user that have carried the video from streaming and the mobile user that have available downlink resource for sharing. The research reduction in streaming costs and better finish, minimum video delivery delays, maximum engine efficiency, and some effects throughput. Other multicasting techniques have further exploited both physical communication feature and social attributes of mobile user to gain higher system performance. However, that study cannot provide the flexible multicasting stress to serve the requesting user that request the video. Field of multicast techniques has been proposed to serve the ISO flexibility by macro-bytesson over conventional cellular transmit and by the caching helper over D2D communication with download resource sharing by the sharing user. The extent problem of the work do not approach the caching play multi-time. Research system capacity is not high. Yes. Solution. So in study, we propose a downlink resource sharing and multi-time caching solution, so-called DRS-MCS solution for video application and service in 5G internet network. Next, in the system model, multicast video streaming in 5G internet network with DRS-MCS are shown in figure. The system consists of one macro-bytesson called MBS, I-femtocell bytesson called FBS, K sharing user called SEO, and G cluster. In cluster G has MG caching helper called GS that have K the request video and NG requesting user called ISO that require the video. The system provides three ways to flexible multicast the video to the multicast from the MBS over conversion serial transmit, multicast from MBS by application channel system apps allocation scheme, and multicast over digital communication by resume the downlink resource sharing by SGO. At the previous time, a number of I/O requests a particular video. The MBS deploy the DRS-MCS sharing includes three steps. Step 1, clustering. Group the GS and I/O that are in close vicinity for digital communication into G cluster to expand to convergent array of its clusters so that there are thus MG GS and NG I/O in cluster. Step 2, DRS-MCS optimization problem. The MBS feature collects the system parameters such as a number of zero and channel information from MBS and FBS and GS to the I/O from MBS and GS to SU. Their parameter enable the MBS to formulate the DRS-MCS optimization problem and show it for optimal downlink resource sharing. Their parameter enable the MBS formula DRS-MCS optimization problem and shown it for optimal downlink resource sharing index VGMK approach to 1 SUK share or 0 not share. The DRS-MCS optimization problem concerns the constraint such as an SU can share its downlink resource with up to only one in whole system and target greater than or equal to given thresholds. Step 3, multicasting. After solving the DRS-MCS optimization problem, the MBS decide which one is channel an FBS or GS multicast the video to on the ISO in the cluster. Next, in the system formalization, to obtain the video capacity delay to the ISO, it is required to compute the signal to interpretation plus noise ratio from the GSM to IUN, the signal to noise ratio from MBS to the IUN, and the signal to noise ratio from FPSI to IUN, and wireless channel. Based on channel capacity, so system capacity is to limit the interference impact on the SEO for high quality is necessary to compute SI and as SUK. Now, DRS MCS optimization problem and solution are present in this slide. First, optimal problem, maximizing object efficiency with constraint. As you can share each downlink resource with up to only one CH in the whole system. And there is up to only as you share downlink resource with one CH in cluster. And the terrorist SINR gamma 0 is considered to guarantee the quality of service of the SU. Next, optimal problem is solved by using exhaustive binary searching algorithm present in algorithm 1. Advance of algorithm 1 is simple implementation for exact optimal result. The performance evaluation is present in this section. The system parameters used to deploy the DRS MCS strategy for multicast video streaming in 5G wireless network are listed in the table 1. To evaluate the performance of proposed DRS solution, we compare each other scheme includes non-DRS without downlink resource sharing. We do not consider sharing the downlink resource of the SU. Only MBS, OMBS. The RU are traditionally served by MBS. And average capacity, we compute the average capacity and minimum capacity mean. We compute the minimum capacity up on the permutation in research space that satisfies the constraint. System performance versus the number of clusters G are shown as feature. This figure shows you increasing G field the high number of I/O service by MBS, APS, and D2D multicast communication, and thus proving the I/O with higher system capacity. If Z equals 1, the performance of all schemes are the same since the packaging place selected to serve the I/O in MBS. And the DRS MCS outperform the other because to more caching place selection opportunity. Next, system performance versus the number of SU are shown as figure. As you can see, if there is no SU K equals 0 to share the downlink resource, the performance of DRS MCS either mean non-DRC are the same, but it higher OMBS than the existing of FBS. Increasing K provide more downlink resource sharing opportunity to increasing performance of DCS and IVR. The system performance gets saturated when K is high enough. For example, K equals 3. That have the system design consider selecting a proposed number of SEO for high capacity as reasonable computation cost. Next, system performance versus the number of FPS. We can observe that if there is no FPS I equals 0, the mean and non-DRS opportunity become OMBS due to no FPS or no DRS assisted. The performance of DRS MCS ever mean and non-DRS increasing in accordance with the increasing of eyes. But getting saturated if is high enough. For example, I equals 4. New FPS are not better in terms of providing higher system capacity than the existing one. So, must carefully consider selecting provide number of FPS to gain high quality system at reasonable cost of computation resource and system architect modification. And final, system performance versus the choice SI and gamma 0. Increasing gamma 0 to 1 is the QoS of SEO reduce the downlink resource sharing opportunity. As a result, the performance of DRS, MCS, and IVR is reduced. When gamma 0 occurs 25 decibels, The performance of this DRS MCS and error is reduced to that of mean and non-DRS. The proper value of gamma 0 should be carefully selected so that the system quality is high enough while wanting the SEO a high quality. For example, gamma 0 equals 5 dB. And finally, I would like to conclude by we have proposed the DRS MCS solution for video streaming application and service in 5G ultra network. We propose DRS MCS not only allow the real audio receive video flexibility multicast from 3 child catching play, ambient, and cheers, but also enable to pair the SU that has available downlink resource with GHz of the video for digital multicast communication by receive sharing downlink resource. The object of the MCS solution is serve the IU the high system capacity while warranty the QoS of SU. And useful circuit for system design and modification are provided to achieve the most effective DRS MCS solution. Well, that's it from me. Thank you.
Ladies and gentlemen, I am Valam Nguyen. I will present the topic performance analysis of realization on cooperative uplink NOMA network with wireless power transfer. Introduction. Future wireless network such as the Bayern 5th channel or 6th channel cellular network are expected to support extremely high data rates up to 1 Gbps and a very large number of nodes up to 1 million nodes per 1 square kilometer with a variety of applications and service. The most prominent candidates that can meet their requirement of Bayern's 5th channel and or 6th channel is a non-orthogonal multiple access NOMA technique. NOMA allows multiple users to share the same resource. Example, a time, frequency, resource block, and separating the user in other domain with some additional receiver complexity. With an explosion in the number of devices in the 5-channel network and future wireless network, leading to the grand need for the power supply for them. One of the methods that attracts the attention of both academic and the industry is radio frequency energy harvesting, which enables the converting of the received radio frequency signal into the electricity energy. This is one of the technical that helps solve the energy problem in the wireless network with a larger number of devices. This article will investigate the performance of realization on cooperative uplink NOMA network with wireless power transfer network and the channel model. Fifth one is a model of an uplink cooperative NOMA system in which the signal are transmitted from the two NOMA users, near user 1 and far user 2, to the bidirectional X with the cooperative of energy constraint, amplifier and forward relay nodes are. Assuming that our user and relay nodes are single antenna device and operated in half-duplex node model. The relay nodes are locate closer to the base station than the user. With two users, the one that has shorter distance to the base station is named as use 1, the farther one is use 2. At the beginning of edge transmission, the channel information from edge to the relay is collected by the base station using pilot signal, whereby edge identify the relay with the best ability to receive energy to specify it the relay node from the user to the base station. The protocol for this system is as follows. In the first file or transfer file, by on relay firing channel configuration from link S to relay nodes R, hash R, actual the relay nodes R, which has the best relay firing channel configuration hash R, the transmit radio frequency energy with the power PL in the alpha T, where alpha less 1 and alpha equal 0 denote the time switching radio and T is block time. The energy gain at the relay during alpha T can be decided by S equation 1. In the second file, information transmission file, use 1 and use 2 broadcast their signal S1, S2 to S and R. S is the base station, R is the relay, base relay, on the same frequency block, following the NOMA schema within the duration of one such alpha multiple T divided 2. The SINR for the text, the signal from this one, the same equation 2, and SNR for the text, the signal from this 2, the same equation 3. In the third file, relay file, R, the base relay R, apply the receive signal and forward to S in remaining time of one such alpha multiple T divided 2, which the energy harvested from S by user the base relay firing channel conference R. The SINR to detect S1 and SS in this file is expressed as the equation A, and the SINR to detect S2 SS in this file is equation 9. The SINR and SNR to detect S1 and S2 in this file, the equation 10 and equation 11. Performance analysis. Proposition 1. Unreliable firing the outlet probability PLS1 for the test S1 is given by equation 22 and 23. Proposition 2. Unreliable firing. Under reliable firing, the outlet probability PLS2 for the testing S2 is given by equation 24, respectively. Proposition 3. The throughput expression for use 1 and use 2 are respectively given by equation 25 and 26. Number result and discussion. The first result, first 2 and first 3 show the system performance result, which are particularly the outlet probability and the throughput at use 1 and use 2 in comparison with transmit power at the bitation P1 with different values of the transmit power at use 1 P1 and use 2 P2. Specifically, from Fig 2, we can see that the always probability as use 1 and use 2 decreases when increasing PL. At the same time, when P2 increases, the use performance reduced as a result because of the increase in interfrequency. This is explained in Formula 2 and Formula A. Similar conclusions are also obtained in case of considering the out probability for user 2 in Fig 2. Specifically, the system performance at user 2 improve if we increase the P2 and decrease the P1, as shown in the Formula 3 and Formula 9. In Fig 3, the towers of both use 1 and use 2 improve when increasing B0. In this result, we also see that when increasing B1 and decreasing B2, the throughput of use 1 increasing. In contrast, the throughput of use 2 increasing when increasing P2 and decreasing P1. The next, the number of relay nodes is also an important parameter of system. Fig 4 and Fig 5 show the effect of the number of relays on the performance of the system in terms of always probability and throughput. In Fig 4, the always probability of the both user decreases when increasing the number of relays. On the contrary, the throughput of both users increases in Fig 5 when the number of relays increases. Through the above two results, we conclude that the performance of system improves when increasing the number of relays. Fig 6 and simulation result of out probability of both use 1 and use 2 following the energy conversion efficiency. We see that the out probability desired with the increasing of the energy conversion efficiency. It means that the performance of the substance in terms of the out probability is improved by increasing this parameter. Fig 7 shows that the throughput of both use 1 and use 2 increases with an increase in energy conversion efficiency. That's the reason for the two results in Fig 6 and Fig 7 is that as the energy conversion efficiency increase, the energy for amplifying and forwarding SR increase. Thus, the signal transfer efficiency at the uplink of the system increase. The impact of time switching ratio one system performance in the term of out probability is illustrated in the Fig A. Results show that with the simulation parameter decided based on the table and the value PL is tending 5 TB, PL1 3 TB, PL2 3 TB. Eta 0 not A when increasing alpha bigger 0 until 0 not 1. The out probability of the both use 1 and use 2 decreases. Then with the value of alpha where alpha bigger 0 not 1 progressing to 1. The average probability of both use 1 and use 2 increases. Therefore, we find that there are value of time switching ratio with the average average probability is the minimum. The allowed term for the finding value of the time switching ratio minimize the average probability. This system will continue to be studied in the future. The system performance simulation result in terms of throughput when alpha where the perform in this night. With performing a throughput simulation of both use 1 and use 2, it can be observed that their throughput is reduced when they increase the value of time switching ratio. Conclusion: we investigate the performance of the network model at about uplink cooperative NOMA network with wireless ball transfer. The cloud form expression for the average probability and throughput of finding out is based on the channel random parameter. Our analysis is confirmed by multiple simulation. Investigate system performance by the key parameter of system. The performance of the use 1 can be improved when increasing B0, P1, the number of relay N and eta, and decreasing B2. The performance of the performance of the U2 can be improved when increasing the PL, P2, the relay nodes and eta, and decreasing P1. Yeah, question and answer. Thank you. Wow.
Good day, scientists and researchers. My name is Dong-Seong, a researcher from Kumo National Institute of Technology in Gumi City of South Korea. On behalf of the co-authors, today I would like to introduce our work on topic, convolutional neural network-based DOA estimation using non-uniform linear array for multipath channels. To convenience, I will present our work follows by the outline points as shown on the slide. In the introduction, I introduce the application of DOA estimation and methods that can be applied for the DOA estimation task. Subsequently, the problem statement of DOA estimation will be mentioned. Then, I show the motivation for our work. From that, we propose a novel solution/method to solve the limitation of the existing methods. Regarding the paper framework, we present a signal model of the antenna array, on which we generate the dataset for training and testing. Next, we design a convolutional neural network for the DOA estimation task, so-called DOA ConvNet. The network is trained and tested with a synthesized dataset under the impairment of Gaussian noise and multipath propagation conditions. Through experiment results, we can evaluate and discuss the DOA estimation performance. Finally, my presentation will be finalized with a conclusion and toward future work. Many years, direction of arrival, or DOA, estimation has been an active research topic for application in various areas, including radar, sonar, and communication. In military radar and sonar systems, DOA estimation facilitates determining the location of targets to help for surveillance, tracking, and control in the ground, air, and water areas of nations. In communications, the quality of wireless connections is greatly improved if DOA estimation is employed to target the user. In many contexts, the DOA estimation plays a role as a spatial filter. In addition, the arrival angle information of a signal source in the electronic warfare operation is very useful to explore further data about the enemy situation, that enables us to build a plan or decide a proper activity. In practice, there are many feasible methods for DOA estimation. We can divide them into three categories. First category is signal parameter-based methods, or traditional methods, that include amplitude, phase, and dual methods, or combination of them. These methods have advantages because of their simplicity, but they generally have limited accuracy. Second category is subspace decomposition methods, typically are MVDR, music, and Esprit methods. These methods provide very high accuracy and resolution, but they have two significant disadvantages. First, DOA pre-estimates of the incident signals are required for spectral focusing, and the precision of those pre-estimates largely influences the performance of DOA estimation. Second, they need the a priori information of the incident signal number, which may not be available, especially in the non-cooperative scenarios. The third category is machine learning and deep learning-based methods, or data-driven methods. The typical models that can be applied for the DOA estimation are support vector regression, deep neural network, and convolutional neural network. Recently, the machine learning technique is introduced as an effective approach to solving the DOA estimation problem. For example, support vector machine, SVM, is used to estimate DOA of multiple plane waves. As part of machine learning, deep learning is a well-known universal approximation theorem that can learn features deeply by designing neural networks with multiple hidden layers. Despite enhancing DOA estimation accuracy, the multi-layer perception consumes a high computational complexity, expensive architecture, and time delay. Besides, convolutional neural network, CNN, allow learning feature automatically without expert knowledge in a specific domain. The problem statement of DOA estimation can be taken into account, including accuracy, resolution, time-consuming, memory-consuming, physical hardware cost, coherence of incoming signals, number of detectable signals, and affective multipath propagation conditions. Those problems motivate us to improve the DOA estimation accuracy and resolution, reduce time and memory consuming, reduce the physical hardware cost, estimate both coherent and non-coherent signals, maximize the number of detectable signals, and eliminate the multipath propagation effect. Therefore, we propose a new CNN model, namely DOA ConvNet, for DOA estimation. And, we also propose a non-uniform linear array with symmetric configuration. Our proposal has some advantages of low cost of hardware components, low computational complexity, improvement angle estimation accuracy, elimination of multipath effects, and it is promising potential for DOA estimation of multiple no-coherent and coherent signals. Our model can be extended for antenna arrays with complex configurations. The figure on the slide illustrates a signal model of a linear antenna array. In principle, incoming signals are captured by the antenna array. Then, the received signals of elements are pre-processed at pre-processing block, and converted to digital form at ADC conversion and data store block. In the digital signal processing block, the signals are reconstructed and prepared for DOA ConvNet. The output of DOA ConvNet is a DOA value of the received signal. Along with other signal parameters, the estimated DOA is indicated in a display for surveillance and tracking. The output signals of array is denoted by vector x, which is calculated by the equation, where n is noise, s is signal of emitter, and a is steering matrix of the array. M is number of elements, and k is number of signal. Based on signal model, we generate a dataset, in which we design the array with configuration of NLA, d equals 0, 3, 5, 7, 10 lambda per 2. The signal source has carrier frequency of 35 MHz. The receiver of direction finding system has analog to digital converter operating at sample frequency of 350 MHz. We suppose that the signal that travels from the transmitter to receiver through 6 propagation paths, with delays in uniform distribution from 1 to 1000 nanoseconds, and attenuation in uniform from -100 to -10 decibels. The Gaussian noise that we assign change from -20 to 25 decibels. with steps of 5 decibels. The angles of arrival are assumed from -89 to 89 degrees, with steps of 1 degree. Therefore, the number of angle classes is 179. The data size of one signal window is of 5 by 256 by 2, where 5 stands for number of antenna elements, 256 presents number of samples per window per signal, and 2 stands for I and Q channels. The dataset has 1,790,000 observation maps, in which 80% is used for training, and 20% is for validation. Inspired by the ResNet architecture, our deep neural network model, namely DOA-ConvNet, is designed with a primary flow, or main backbone path, and skip connections, residual paths, as shown in Figure A on the slide. Accordingly, the primary flow is constructed by a series of conv blocks that are connected to each other consecutively from input to output layers. Each conv block, as shown in Figure B, consists of 2 branches, whose outputs are synthesized by an addition layer. Each branch contains 2 consecutive one-dimensional convolution layers, 1 max pool layer, and 1 ELU activation function layer. We can observe that 2 one-dimensional convolution layers, with filter sizes of 1 times k and k times 1, are employed instead of 1 convolution layer with a filter size of k times k. This way helps to reduce the number of learnable parameters that produce the model with a light-await structure. In the second branch, 2 convolution layers with 2 mentioned kernel sizes are exchanged their positions. The second convolution layer is followed by a max pool layer, whose hyperparameters are designed by a pool size of 1 times 3, and stride of 1, 2. The role of max pool layer is to perform downsampling to reduce the size of feature maps, and extract the robust features before going to the activation layer. The activation function plays a crucial role in CNNs as a brain neuron, which activates the useful features and impairs the redundant ones. In our model, we use an exponential linear unit function, a smooth activation function, which provides better signal propagation through the network than ReLU1. The ELU function is expressed as on the slide, where Y denotes the output, X stands for input value, and alpha is a scalar number between 0.1 and 0.3. In this work, it is chosen by 0.2. Now, we discuss the experiment results. Our model is intended with changeable hyperparameters, including number of conv blocks, number of filters, and size of filters. Different configurations of the model will be evaluated, and then a suitable one will be chosen for competing with other existing models in terms of accuracy and time consuming. For each configuration, the model must be trained with the synthesized dataset, as mentioned before. For evaluating the impact of filter size on the performance, the network is configured with following hyperparameters: 5 conv blocks, 64 filters per convolution layer, and various filter sizes with k equals 3, 5, 7, and 9. The experimental result presented in figure on the slide shows the comparison of angle classification accuracy, that depends on various SNR levels, and different convolution filter sizes. It shows that in spite of giving the best accuracy at low SNR levels, from -20 decibels to 0 decibels, the model with the filter size of 1 times 9 has the worst performance at high SNRs, greater than 0 decibels. Whereas, the model with the filter size of 1 times 3 seem lowest correct angle classification rate for SNR below 0 decibels, but it outperforms other ones at higher SNRs excepting 1 times 7. By observation, the model with the filter size of 1 times 7 obtains very good performance at all SNR values. Especially it achieves the best accuracy with SNR greater than 0 decibels. In previous evaluation, the filter size with k equals 7 is selected as a suitable configuration of the convolution dimension. Thus, the second experiment is performed with different numbers of filters in a convolution layer, while 5 conv blocks are still used in this evaluation. As a result, figure on the slide shows the different performances of the model due to various filter numbers. Logically, more filters result in more neurons in the model, thus, more representative information should be extracted for better prediction performance. However, we observe that the model with a greater number of filters does not gain higher angle classification accuracy, that the number of filters should be satisfied with dataset properties that only be discovered by experiments. In particular, in this framework the model with 48 filters estimates DOA with the highest accuracy, whereas the models with 64 and 96 filters obtain lower performance. How many convolution layers are optimal for a neural network model-based DOA estimation is always a difficult question for answering. Indeed, how big is the network? It depends on the dataset properties and the number of output classes. Therefore, a classifier must be fitted with a particular dataset. For the DOA estimation problem, DOA ConvNet also has to be optimized with a suitable number of convolution layers, which must obtain good accuracy and fast execution. Herein, the number of convolution layers is represented by the number of conv blocks. By experiment, the accuracy performance depending on SNRs and different numbers of conv blocks is shown in figure on the slide, which shows that DOA ConvNet with 5, 6, and 7 conv blocks achieves the almost same classification efficiency and significantly better than that with 3 and 4 conv blocks. Moreover, the execution time performance also is taken into account for assessment. This result is listed in table, where the numerical results enable us to suggest that the model with 5 conv blocks is chosen to satisfy the accuracy, structural, and time cost requirements. As a result of the aforementioned analysis, DOA ConvNet with 5 conv blocks, 48 filters, and a filter size with k equals 7 is our designated DOA ConvNet to compete with 2 other existing ones, namely DOA CNN1 and DOA CNN2, for DOA estimation task. DOA CNN1 consists of 4 consecutive pairs of conv plus ReLU layers, following by 3 fully connected layers with output sizes of 512 for 2 first ones and 179 classes for the last one, and finalized by softmax layer and output decision layer. DOA CNN2 is constructed by 4 consecutive pairs of conv plus ReLU layers also, but its input data is a spatial spectrum, which is pre-processed by beamforming technique. Both mentioned CNN models were demonstrated remarkable outcomes in their own case studies. In this comparison, we applied those 2 CNN models for our signal dataset design, based on 5-element 10LA along with Gaussian noise and multipath channels, to compare with DOA ConvNet, while other setting up parameters remain as original. Regarding the structural volume, DOA CNN1 and DOA CNN2 have respectively 8,662,451 and 960,488 learnable parameters, whereas DOA ConvNet has the number of parameters of only 646,619 only. However, in the accuracy comparison, DOA ConvNet gains the highest performance at all SNR values, the second place for DOA CNN1, and the worst for DOA CNN2. As we mentioned above, DOA ConvNet is designed for reusage of former feature maps, which can improve the robust features, therefore, it achieves higher accuracy. In conclusion, we have demonstrated a novel CNN model for DOA estimation. DOA ConvNet has been evaluated based on different structural hyperparameters by experiments to gain an optimal one with a good trade-off between accuracy and structural. A new dataset was synthesized with consideration of both Gaussian noise and multipath channels. DOA ConvNet has remarkably outperformed 2 existing models for the same DOA estimation task when experimenting on our dataset. For future work, we intend to develop the network for different array geometries, such as circular, rectangle planar, or spherical arrays, which can estimate signal DOA in both azimuth and elevation planes. We would like to thank the National Research Foundation of Korea for supporting us in this international cooperation work. Thank you for your attention. Now it is time for question. For offline discussion, please contact us via the email address.
Hello everyone, my name is Hoàng. I'm from Hanoi University of Mining and Geology. Today I'm going to present a paper entitled UAV and Distributed STBC for Wireless Relay Networks in Search and Rescue Operation. I begin with the outline. My presentation is divided into 5 main parts. After introduction, I'll give you the information about distributed STBC cooperative diversity system, and then I will present the proposed method. Performance evaluation is will follow, and the presentation will end with conclusion. The following is the introduction. UAV communications share the common feature with MANET, such as independent, dynamic, and self-adaptive nature. In addition, UAVs they can adjust their attitude to avoid obstacles and enhance the likelihood of establishing line of sight links to ground user. UAVs they can also operate as relays to provide connectivity with two distant users for improving transmission performance and coverage area. Therefore, UAV communications are suitable solution for search and rescue operation. However, in multiple wireless networks with UAVs like figure 1.1, due to the communication distance or obstacles such as trees, hills, and mountains, and so on, the several links between adjacency nodes can be disconnected. The end-to-end performance can be derived based on the performance of the equivalent single hop with the minimum output SNR in the network. In order to improve the end-to-end performance, OFDM and STBC schemes have proposed as a good candidate to obtain reliable and high performance. In this paper, UAV is first considered to add to the hop with the minimum output SNR and operates as a relay to improve the transmission performance. In addition, the origin STBC patterns is modified in order to use in UAV communications, and finally, an algorithm is proposed to find out the optimal location of the added UAV. Now, I would like to move on to distributed STBC cooperative diversity system with analysis. Distributed STBC is considered to use in UAV communication because STBC can obtain the higher cooperative diversity gain without channel state information. Furthermore, it can achieve both the full diversity order or full data transmission rate with simple decoding algorithm at the receiver. The diversity gain can also be obtained by using distributed relays in cooperative system. Here is the model of the distributed STBC system with 2 transmit antennas and 1 receive antenna. And here is a table of STBC pattern for the model with 2 adjacency symbol Sj and Sj plus 1. Next is the signal analysis of STBC encoding. The equation 2.1 is the received signals of the Sj and Sj plus 1 symbols at the ith receiver. At Here is channel response. N is the noise component. The received signals are represented in terms of vector and matrix as the equation 2.2 and 2.3 respectively. It also can be equivalently expressed as equation 2.4 and 2.5. The combined signals can be written as equation 2.6 and 2.7. Finally, the signal is decoded by maximum likelihood detector. Next, I'm going to present the proposed methods in more detail. The first is the transmission method and the modified STBC patterns. In phase 1, the signal is transmitted from the transmitter to UAV and the receiver. Equation 3.1 is the received signals at the UAV and the receiver respectively. In phase 2, at the UAV, the signal is first decoded and then re-encoded and forwarded to the receiver. At the transmitter, the signal is also retransmitted simultaneously to the receiver. At the receiver, the signals are combined at equation 3.2. Table 2 shows how STBC pattern is modified. The signal is not changed at the transmitter, but it is only changed in the UAV. Equation 3.3 represents the received signals in terms of vector, and the orthogonality of modified STBC encoding pattern is proved at equation 3.4. Equation 3.5 is the decoded signal. After that, the signal is sent to detector. Indicate that the received signal in phase 1 is stored and compiled with the received signal in phase 2 at the receiver. Equation 3.6 represents the signal of this case. The decoded signal are derived as the equation 3.7. Finally, the signal is sent to the maximum likelihood detector. Now, I would like to move on to algorithm of finding the optimal location of the UAV. The algorithm is based on the performance of the control package in order to find out the optimal location of the UAV before transmitting data package. With the assumptions as mentioned in the paper about the channel model and a fixed transmission power level for all nodes, system performance or bit error rate can be expressed by the empirical function as equation 3.8. Equation 3. Equations from 3.9 to 3.11 are the SNR of the received signals at the receiver and UAV. Equation 3.12 is the SNR of received signal at the receiver when UAV transmitting the symbols with STBC encoding. J is the STBC cooperative diversity gain. This table describes the algorithm in detail. The input is the location of transmitter and receiver. The output is the value of X and L. X and L are determined so that the SNR is the maximum at the receiver, like equation 3.12. Next, I'm going to talk about the performance evaluation of the proposed methods. Here are the simulation conditions. The distance from the transmitter to receiver is set to 300 meters, and it is normalized to 1. And the horizontal sub-boundary is set from 0.15 to 0.85. The vertical sub-boundary is set from 1.5 meter to 100 meter. The other simulation conditions are listed in table 3. Here is the simulation results. The figure above of the proposed methods with different location of the UAV x star is equal to 0.15 to xn is equal to 0.85 and else is fixed to 0.5. From the figure, since the receiver is out of the transmission range of the transmitter, direct transmission does not achieve a good performance, only approximately 10 power minus 2. When an UAV operates at a relay, the performance is improved significantly in comparison with that of direct transmission. It can be seen that the best performance can be obtained when the location of UAV is in the middle. X is equal to 0.45. This is because thus the signal from the transmitter is received and decoded by the UAV, then forwarded to the receiver and channels, and the channel is the semantic fading channels. Due to the STBC cooperative diversity gain, and UAV transmission with STBC encoding has much better performance than UAV transmitting without STBC encoding. From the figure, the best performance can be obtained when the location of UAV is about 60 meters from transmitter, or X is equal to 0.2. This is because the signal is encoded according to table 2 as transmitted from both the UAV and then the transmitter to the receiver in phase 2. Therefore, STBC cooperative diversity gain can be obtained, which in turn leads to the significant improvement of performance in phase 2. As a result, the optimal location of UAV on horizontal axis will move to the transmitter depending on the cooperative diversity gain. The signal in phase 1 is stored at the receiver and antenna, combined with the signal in phase 2. From the figure, the performance is better, but the optimal location of UAV is the same. This is because the combining signal leads to higher SNR, but STBC diversity gain does not increase. In this simulation, the vertical location of UAV is varied from 0.1 to 0.9, and X is fixed to 0.2. It can be seen from the figure. The performance decreased slightly when L value increases. The reason is that when L value increases, the distance from the transmitter to the UAV and also from the UAV to the receiver is greater. However, the different distance is quite small. In this simulation, the performance of system with different transmit power is evaluated. From the figure, due to cooperative diversity gain, the UAV transmission with STBC encoding achieves a much better performance than both the direct and then UAV transmission without STBC. The performance is also slightly improved for combining signals stored in the phase one at the receiver. Finally, I conclude my brief presentation. In this paper, first, an UAV is considered to add to the hub with the minimum output SNR and operates at a relay mode to maintain the links between adjacency nodes, expand the coverage area, and improve the performance. In addition, the original STBC patterns are modified while keeping the same operative diversity gain. Furthermore, an algorithm is proposed to find out the optimal location of the added UAV. The optimal location of the UAV depends on not only the environment of real scenarios, but also the cooperative diversity gain. In order to achieve the best performance of system in this scenario, the UAV should be located at 0.2 to 0.3 according to horizontal axis, and from 0.5 to 0.9. Thank you for your attention.
Hi everyone, I am Văn Nule. I come from Reconstruction Technical University. Now I present my paper with title Resolution Improvement of Confocal fluorescence miscopy by two different point spread functions. Now we go to outline, include four parts. The first, introduction. The second, method. 3 and results, and the final conclusion. Now we go to introduction. Because of the diffraction limit, the maximum spatial resolution of traditional optical miscopy in the far field is about, in which lambda is the illumination wavelength and Na is a numerical aperture. The confocal fluorescence miscopy system can be used to achieve the resolution improvement by a factor of. However, the resolution of confocal fluorescence miscopy reached to 200 nano under the recent experimental condition. In order to improve the resolution, the common methods are the use of many light beams that stimulate emission deflection means copy uses two beam. Fluorescence emission different means copy uses two beam. Stochastic optical reconstruction means copy uses many beam. The photo activated localization means copy uses many beams. The final structure illumination means copy uses three beams or five beams or so many beams. In this paper, we propose a new method using two beams to improve the resolution. Now we go to the method. In this paper, we introduce all the method based on the use of two kinds of voice function. The first PF, the second PLF. The two images can be classified using the two voice function. On the image is acquired by employer dot beam, which is modulated by the Gaussian beam. This image equals do not emit. Another image is achieved by using do not beam, which is modulated by the voltage phase mat. This image is called do not emit. The third image is generated by using multiplying relationship between the dot emit and the do not emit by this expression. The image is called multiplying image. Now we introduction to optical layout for permanent experimental result. The first model is shown picture A. It can be seen that two illumination points are shown. The first, the second. The first point is gold beam. The second point is donut. The donut beam is modulated by the voltage phase mat that is generated by a spatial light modulation. Because two beams are separated before SPF, we should carefully adjust the two illumination beams to protect that two voice functions have the same position on the sample. Another model is showing pitch B. In this model, on the spatial line modulation instead to the illumination point of optical system. The SLM can be with different kind of phase path. When we want to use a dot beam, the SLM will generate the zero phase mask. When we want to employ the donut beam, the SLM will produce voltage phase mask. I can be see that the step of optical in the figure P is similar in comparison with that in picture A. Therefore, we use a setup of optical system in the PCB for perform experiment. Now we go to simulation and experimental results. In order to highlight the proposed ability for the improvement of the resolution, we perform some simulation results. We use some initial parameter for simulation condition. And the illumination laser, and the sample is placed in the medium for index diffraction of alpha and beta. The first, we consider which spoken image. The original image is shown picture A. The confocal image showing picture B, and probable image is indicate picture C. We draw additionally on blue circle over the confocal image and probable image. The circle is the same variant. From picture B and picture C, I can see that the outside the blue circle, we can insert for the confocal image and probable image. But the inside the blue circle, the confocal image is not discerned. Why some parts of probable image still discerned? This means that the effectiveness of our method for the improvement of the resolution can be achieved. Next, we simulate with cell microtubule. The original image is showing picture B A. Picture B shows the confocal image. Picture C indicates probable image. We can see there are two lines on the original image. At the position on and position 2. That which nearly parallel at the on the original. It can be seen that two lines on the confocal image, which is shown at position 2 on two do not separate. Why the two lines of purple image can be distinct. Let's see question 1. The final, in order to highlight the ability of the resolution improvement of our method, we use a 2 nanometer spherical fluorescence particle to perform experiment. The picture A shows confocal image. The picture B indicates purple image. It can be seen that the size of spherical fluorescence particle of two images is the nearly same. However, the resolution ability of the purple image is better than that of confocal image. This can be clearly shown by drawing a line through a center of particle on picture A and picture B. The line is shown in picture C. From picture C, I can be clearly see that the resolution by using purple method was remarkably improved. We use a full width at half maximum to measure ability resolution. This is more, the resolution is better. From picture C, I can see it answer this and small this answer. This means that the purple method have the improved resolution. The WFM of particle on the purple image is smaller 1.43 times than that of particle on the confocal image. This result demonstrated that our method can be used to improve the resolution of the confocal fluorescence microscopy. The final conclusion. We have proposed a new method using two beams to enhance the resolution of confocal scanning microscopy. A new relationship between two images to obtain the high resolution image is introduced. The effectiveness of proposed method demonstrated by simulation and experimental results. Thank you very much for your attention.
Ladies and gentlemen, I'm Hưng. I'm a PhD student at Lequidon Technical University. On behalf of our group, I'm very happy to present our research results about estimation of matching layers effects on land antenna characteristics. My presentation divided into 4 parts. Part 1, Introduction. Part 2, Theoretical matching layers and antenna modeling. Part 3, I will tell you about simulation results and discussion. The last one's conclusion. Now let's start with introduction. You know, at the millimeter wave frequency, the antenna element size becomes smaller 10 times compared to the sub-6 GHz 5G base station antenna element. This frequency strength allows selecting various antenna elements such as lens antennas, array antennas, and reflector antennas. The reflector antennas with multiple feeds have high direction and the ability to create multi-beams. However, high cross polarization and the side lobe level because these antennas are affected by feed. In recent years, researchers have been an increased interest in using dielectric lens antennas because lens antenna is capable of producing multi-beam and broadband. It's not affected by blockage of the reflector and the feeds, and it allows electric waves from the front to penetrate backwards. Lens antenna has been studied and applied to many kinds of broadband communication systems, such as K-band, Q-band, V-band, and so on. In the electric lens antenna application, choosing the relative permittivity of the lens material is very important because it has a major influence on the antenna radiation characteristics. Thus, the electric materials enhance the efficiency of transmission energy through the lens and improve the front to back radiation ratio of the lens antenna. However, the dense dielectric material in the lens antenna causes reflection on lens surface and in the lens. It may reduce gain, beam distortion, and increase side lobe level. So, using matching layers to lessen the unwanted effects. So, in this paper, we study effects of high-density dielectric materials used to make typical lenses, such as Teflon, mica, alumina, and silicon. We also perform a theoretical calculation of the power reflection coefficient and the simulation in the electromagnetic environment, thereby making accurate evaluation of specific impact of each dielectric material type. Now, let's continue with part 2, theoretical matching layers and antenna modeling. The figure shows the matching layer is assigned between the airs and the dielectric region. Region 1 denotes the air. Region 2 is the matching layer, and region 3 denotes the dielectric. The relative effectiveness of the matching layer techniques can be easily assigned by power reflection coefficient. It's given by equation 2, where R12 and R23 are power reflection coefficient at the surface between region 1 and 2, region 2 and 3, respectively. Alpha 2 equals 2b divided to lambda ml, where lambda ml is the wavelength in the matching layer enlargement. Epsilon mL is the relative permittivity of matching layer. If epsilon mL is between values of epsilon 1 and epsilon r, then R12 times R23 is positive. Thereby R changed and served as a function of matching layer thickness. Therefore R reaches the minimum values when these equal quarter wavelength of matching layer and equal 0 when R12 equal R23. Then epsilon mL is a geometric mean of epsilon 1 and epsilon r, or epsilon mL equal square root of epsilon 1 and epsilon r. The thickness of matching layer is defined as equation 3. As can be seen in the figure, the lens antenna structure consists of a conical horn antenna as a wide-angle power and a lens which has a simple structure of a curved surface and a flat surface. It rotates around the oldest axis. The curved surface of lens is the hyperbolic, and it is determined by equation 4. The conical horn antenna is designed to perform at 28 GHz and reach a maximum gain of 15.15 dBi. Lenses are dense dielectric material are Teflon, mica, alumina, and silicon. The theta I and theta r represent the incident angle and refracted angle at the lens surface. This angle satisfies Snell law. The lens is covered with a quarter wavelength matching layer whose structure is shown in the figure. The matching layer has relative permittivity epsilon mL and the thickness d, in which lambda mL is the wavelength inside the matching layer. The rays are radiated from the conical horn antenna in region 1, passing through the matching layer to region 3, and then go out through the other side of lens, forming the rays parallel to the oldest axis. The simulation parameter, computer configuration, and software are shown in the table. The survey is conducted using the ANSYS ADS electromagnetic field simulation software. Now turn to part 3. I will present the simulation results and discussion. The figure shows the effects of the thickness and relative permittivity of matching layer on the power reflection coefficient and the lens antenna. Obviously, when the thickness of matching layer equal to a quarter of the wavelength in matching layer medium, the power reflection coefficient is lowest. When the relative permittivity of the matching layer is equal to the geometric mean of the air and the dielectric substance of length and thickness of matching layer is equal to quarter of the wavelength in the matching layer medium. The power reflection is 0, as illustrated in the figure A. When thickness of matching layer changes, the power reflection coefficient at the interface of the length of the S and layers and the electric of silicon lens is always higher than that of other dielectric material. When epsilon MA not equal to square root of epsilon 1 and epsilon r, the lens antenna cannot eliminate the reflected energy. The radiation pattern of lens antenna with and without the matching layer using the different material are present in the figure. It's easily observed that the lens antenna radiation with the matching layer is better than those of the without the matching layer. Specifically, in absent the matching layer, the lens antenna had highest gain of the 27.07 dBi when Teflon is used as a dielectric, and it reached the highest gain of 25.39 dBi when lens dielectric is mica. Whereas in case of with matching layer, the lens antenna had highest gain of 27.82 dBi with the dielectric of silicon and 27.14 dBi with dielectric of mica. For side lobe level, when the matching layer is attached to lens, the side lobe level of all 4 case decrease. Mica reduced by 7.52 dB from minus 16.69 dB to minus 24.21 dB, followed by silicon dielectric and aluminum at 5 dB and 1.99 dB respectively. Whereas in case of Teflon dielectric, there is a minor change in the side lobe level, only 0.68 dB from minus 25.21 dB to 25.89 dB. For lens thickness, applying equation 3 and 5 and established simulation parameter, we can calculate the thickness of lens. Accordingly, the lens with Teflon dielectric is thickness with 25.17 mm, while lens with the silicon dielectric is thinness with only 7.07 mm. The electric field distribution of the lens antenna with the dielectric Teflon and silicon on the exact plane are shown in the figure. As for silicon lens without the matching layer, the electric field distribution between the lens and the conical horn antenna is rough, even cancel out just before the lens, and the spherical waveform of the feed horn is no longer clear. As for matching layers coated silicon lens, the electric field distribution is quite smooth and more uniform, and flattener waves behind the lens are shown more clearly. The first reason for this field distribution is that silicon has a dense dielectric structure, so the rays from feed horn to the lens surface are reflected more. Another possible explanation is that the curvature of inner surface of lens is less than that of Teflon. Therefore, the rays bounce back toward the feed horn more. Ladies and gentlemen, through the simulation analysis and evaluation results in this paper has demonstrated the role of matching layer in improving the characteristics of a specific dense dielectric lens. The results show that, coupled with matching layer, the silicon dielectrics can improve the maximum gain of 2.2 dB, while the mica dielectrics can reduce the maximum side lobe level of 7.52 dB. In addition, the silicon dielectric lens is 19.1 mm thinner than the Teflon dielectric lens and achieve a higher gain. So this is also the efficiencies of using a matching layer for high density dielectric lens antenna. That's all of my presentation. Thank you for your attention. Thank you.
Hello, I am Lương Duy Mạnh from Lake Quidon Technical University. I'm very pleased to make a presentation today entitled a 3-stack GaN-HEMT power amplifier with independently biased technique in INISCOM 2020 conference via video recording. This is outline of my talk today. First, I'd like to introduce background of this research. Then, the proposed circuit configuration in this study will be described in details in the next section. After that, simulator results in Keysight Idea Simulator will be presented in the following section. The experiment to validate simulated results is presented in the experimental section. Finally, the conclusion section. As you can see in this slide, a conventional 3-stack GaN-HEMT structure has 2 floating potential points between the first and the second transistor, and between the second and the third transistor, as you can see in the left top figure. This will decrease performance of the power amplifier. To sum up this drawback, we propose a new configuration by inserting 2 bias terminals to the floating points. This brings a very promising advantages of independently adjusting bias condition for each transistor, therefore increasing degree of freedom for optimizing performance of the power amplifier. This slide shows a description of how to realize such an independently biased 3-stack GaN-HEMT chip. To save chip space, the proposed configuration will be implemented using an MMIC technology of WIN Semiconductor from Taiwan. Here, bypass capacitors are realized on MIM capacitors, while interconnects among transistors are realized using metal transmission lines. 3 GaN-HEMTs have the same size of 0.25 micrometer multiplied by 0.75 micrometer multiplied by 4 fingers. The total size of the MMIC chip is 674 micrometer multiplied by 1025 micrometer. This slide shows descriptions of the proposed amplifier, which is realized using the 3-stack GaN-HEMT topology as an active device. The MMIC chip is connected to the external components, including input-output matching networks and biasing lines through gold bonding wires with a diameter of 30 micrometer. Input matching network and output matching network are implemented using off-chip lump components from Murata libraries. Gate bias of the first transistor and drain bias of the third transistor are implemented using bias tees, including an RF choke inductor and a block capacitor, CB. In addition, drain bias of the first and the second transistors are implemented using two quarter-wavelength transmission lines. Here, it's note that the input matching network and output matching network are designed to match source and load impedances of the MMIC chip to 50 ohm at only fundamental frequency without using any harmonic termination techniques. The most important feature of the proposed amplifier is the high degree of freedom in bias adjustment of each transistor, leading to the power amplifier performance improvement. In the proposed circuit, the topology, two added bias terminals have been included in order to bias the drain bias terminal of the transistors. As can be seen in the figures, when changing VD1 and VD2, DC power consumption of the proper configuration can be reduced over the conventional one, leading to a possibility of efficiency improvement of the power amplifier. The main contribution of this independent bias control is to recontribute the DC power consumption of the power amplifier. This helps to increase efficiency while ensure sufficient output power, as can be seen in the figures of this slide. When VD1 changes from 3 voltage to 7 voltage, both PAE and Pout can be significantly varied. When VD1 increases, PAE max can be higher than that of the conventional one, while the maximum output power, Pout max, can still remain the same level as the conventional one. To make a superior trade-off between efficiency and output power compared with that of the conventional one, VD1 should be set at 3.53 voltage. The right figure shows us when VD2 changes from 1 to 5 voltage, the maximum PAE first increases and reaches maximum value at the middle regions and drops at high values, while maximum output power increases with the increasing VD2. According to this figure, there remains sufficient output power without degradation of the efficiencies over the conventional one. VD2 is chosen to be 4.0 voltage. This slide shows the dependence of amplifier linearity, which is expressed in terms of the third order in the modulation distortion, IMD3, on the variation of the gate bias voltages. Here, the spacing between two input tone signals is 4 MHz. It can be clearly seen that the first gate bias VG1 affects dominantly to the linearity performance of the amplifier compared to VD2 and VD3. Moreover, VD1 should be set at high values for the linearity improvement. In this slide, investigation of the linearity with variation of the drain bias voltages is carried out. It can be clearly seen that the first drain bias VD1 is a dominant factor for linearity improvement, and this bias voltage should also be set at high values. VD2 and VD3 have almost no effect on the linearity performance improvement of the power amplifier. After careful simulator investigations of the proposed amplifier, these sessions presents experimental validation. This slide shows the picture of the fabricated prototype of the power amplifier, which is realized from the proposed three-stage configurations. Bias terminals of the gate of the first transistor and the drain of the third transistor are not shown in the figure. Female and male SMA connectors function as the input and output ports, respectively. The prototype was fabricated on a Metron 6 substrate from Panasonic with following parameters. Dielectric constant is 3.7. Substrate thickness is 0.75 mm. Dispersion factor is 0.002 and the copper thickness is 35 micrometer. In the measurement of the power amplifier prototype, bias conditions of each transistor, which are found from the previous session, are used. The bias conditions for the proposed configuration are as follows. VG is minus 2.7 voltage. VD1 is 5.5 voltage. VD2 is 4.0 voltage. And VD3 is 17 voltage. This slide shows the experimental setup for the large signal measurement of the power amplifier prototype. A microwave signal generator is employed to input the RF signal to the power amplifier at an operation frequency of 1.6 GHz. Two BSD symbols are clearly visible in the figure. Two RF directional couplers are used to split input and output RF signals to make input and output power measurement. Power measurement is made by using power sensors combined with a power meter. All components for power measurement are carefully calibrated prior to make actual measurements. A spectrum analyzer is employed at the output to check the output spectrum as well as to verify if the power amplifier is unintentionally oscillated during the large signal measurement. The measure large signal performance including efficiency, output power, and power gain, as well as the third order in the modulation distortion IMD3 are shown in this slide. Power amplifier is biased at the optimum bias condition, which is found from the previous sections. The proposed power amplifier can operate in either efficiency mode or linearity mode by simply adjusting bias condition of each transistor. In the efficiency mode, the practical bias condition is given as follows. VG is minus 2.7 voltage. VD1 is 5.5 voltage. VD2 is 4.0 voltage. And VD3 is 17.5 voltage. In the linearity mode, for high linearity performance, one can adjust VG as well as PD1 and PD3 slightly to obtain good performance for the linearity. This demonstrates interesting feature of the proposed power amplifier. Finally, I'd like to conclude my talk. In this study, we have proposed a novel circuit configuration in the device level to both improve efficiency and linearity of the power amplifier. The proposed configuration occupies just a compact space thanks to using MMIC technology. The proposed power amplifier can operate either in efficiency mode for high efficiency or in the linearity mode for high linearity. This means the power amplifier exhibits superior performance over the conventional power amplifier, making it very suitable for the next generation wireless communication systems. And thank you very much for your attention.
Hello everyone. Today I would like to present our main research result in the article called Feasibility and Design Trade-off of Neural Network Accelerator Implemented on Reconfigurable Hardware. As we know, FPGA recently has gradually become a viable alternative to GPU-CPU platform for implementing neural network. This would analyze utilization, accuracy, performance trade-off in the hardware implementation for neural network using FPGA and the feasibility of applying the design in reality. The main result of this course are: first, a generic architecture of the single neural network layer has developed and implemented on FPGA for MNIST and Keep-10 datasets. Second, outstanding result when implementing neural network on hardware compared to implementation on the software, up to 20,000 times faster, while accuracy deviations are negligible. Let's talk about the basic structure of the neural network. In this paper, we use neural network for image recognition tasks on MNIST and Keep-10 datasets. Generally, a fully connected neural network consists of three consecutive layers: input layer, hidden layer, and the output layers. Input features here is image data are collected and fed into the input layer. Then input feature and are fully connected to hidden layer that learns the underlying pattern of the input data. Finally, the hidden features are progressively propagated to the output layer which provide predicted label. This work considers the case study of the image recognition task on MNIST and Keep-10 datasets. Fully connected neural network have shown promising performance on image classification. However, with large and high resolution image inputs, the fully connected neural network require large memory size to store chaining parameter and high performance computing units. Therefore, a more effective network architecture should be designed to overcome the drawback of the fully connected layer and fully connected neural network. Therefore, convolutional neural network (CNN) were invented for achieving superhuman performance on complex visual tasks. In this work, we conduct modeling neural network using the programming language Python and TensorFlow library running on the Ubuntu 16.04 64-bit operating system as a software platform to conduct model training and evaluation of the indoor image recognition result. We conduct the study on the impact of the design parameters on the accuracy of the model. We consider the following 4 cases to calculate the accuracy: 1 layer, 2 layer, 3 layer, and 4 layers. Based on the result obtained on the graph, it can be seen that image recognition accuracy in the MNIST dataset is relatively high compared to object classification accuracy in the Keynote dataset. Also, the average time is to recognize MNIST image is relatively lower compared to the Keynote image. About performance evaluation of neural network on a software tool. Implementing floating point arithmetic operation on hardware is inherently complicated and area inefficient. Therefore, we need to look for an alternative way to implement a neural network-based classification model on hardware. For both MNIST and Keynote dataset, as shown in both two figures, the volumetric element values are fundamentally concentrated in the range -0.25 up to 0.25 compared to the floating point number single precision and 8-bit fixed point number would realistically reduce the design complexity and resource usage. About design of neural network accelerator or FPGA, first we introduce a standard and fully parameterized hardware architecture designed for single neural network layer. Then this fundamental design can be used to construct the full complex neural network with an arbitrary number of hidden layers. For this layer, there are multiple processing units, including multiplier, accumulator, mark, adder, activation, and memory buffer for input, output, and changing parameter. To reduce the computational complexity of hardware architecture, the changing parameters, including weight and matrices, are learned and using the neural network software tool and are stored in the memory of the hardware. In this section, we introduce a standard fully parameterized hardware architecture designed for a single neural network layer as shown in the figure. Assume that each mark unit corresponds to multiplication between two binary numbers, an input feature and a weight value. During a clock cycle, an input feature and a column of weight metric are multiplied in a parallel using NI plus 1 mark. To complete multiplication between the input vector and the weight metric, NI clock cycle corresponding to NI input features are required. The mark output called spectral CK is calculated like the formula on the slide. In this section, we talk about the meaning of the parallel coefficient. To reduce multiplication between the input vector and the weight metric, NI clock cycle corresponding to NI input feature are required. To reduce the number of clock cycles needed for metric multiplication, it is possible to to read J input and J columns of the weight matrix at the same time. The required number of the clock periods for the matrix multiplication can be reduced by a factor of J. The number of marks in a clock cycle will increase accordingly by P equal Ni divided by J time. The value of the parallel vector P is called the parallel coefficient. Let's talk about the design of the data buffer. The input data buffer has memory cell arranged in row and operates under the FIFO mechanism. The FIFO, which is equal to the number of bits for input representation multiplied by the parallel coefficient P. Recall that the weight matrix is optimized during the training process implemented by the software tool, since parameter learning consumes a lot of hardware resource. The value of the weight matrix can be represented by the k-bit binary number, similar to the organization of the input buffer memory. The data width of the weight memory has to be matched to design a parallel coefficient. The bias matrix ejected from the training phase of the classification model is a vector similarly to weight value X bias element needs k-bit to represent. The output data buffer with the FIFO mechanism is designed to store the result of the multiplier accumulator vector of n I plus 1. We introduce to consider dataset and describe the neural network architecture for each data. Based on the generic model described on the previous session, we have implemented the hardware model targeted for MNIST and FIBA10 datasets. For the MNIST dataset, each input image will be converted to a 1 by 784 binary matrix. Input matrix and the network parameter with and bias value obtained from the training phase on the software are fed into the silent payload simulator to collect performance metrics including computational speed and recognition accuracy. In case of FIBA10 dataset, to simplify the hardware design, only fully connected layers are implemented on the hardware, while feature each layer are pre-processed. To examine the performance of the hardware design of the neural network accelerator, we have collected the performance of the image classification model on the real FPGA board. Our entire generic design has been described by a hardware description language where the number format and parallel coefficient are considered by a design parameter and can be set to design a value. The result of image recognition accuracy with different parameters are shown in the table 1. We focus on analyzing the dependence of recognition accuracy on two main parameters, the number of hidden layers and number format to represent the value of the weight matrix. It can be seen that the classification accuracy depends on more on the number of format than the number of hidden layers. From the table 1, we observe that the 8-bit format can be used to save hardware resources while ensuring accurate performance on image classification. And full comparative figures between image recognition and all hardware and software are given in table 2. From this table, we observe that the time to recognize image when performing on hardware is faster than image recognition on software at least 1,500 times when the parallel coefficient equals 1 and may be factor up to 20,000 times when the parallel coefficient equals 16. In this work, we have chosen some representative and active episode families from Saling, including the low-cost RT7, the best price performance Kintex 7, the performance optimized Protect 7 with different resource capability. In terms of resources, except for the RTX XC7A 1000T episode, where all DSP is fully utilized, the remaining episode devices are considered large enough for accommodating two-layer neural network in either cipher or ENISC. In terms of performance, the achievable clock frequency are technically dependent mainly on the latency of mark. Therefore, the reported clock frequency ranges from 153 MHz RTX7 to 200 MHz Protect7. Furthermore, we evaluated the impact of the parallel coefficient on the resource utilization and bandwidth of the hardware architecture. The figures present the resource utilization for the case of ENISC implementation on the Saling Kintex 7 episode series XC7K325T. Based on the result obtained, we found that the image recognition speed also increased almost proportionally to the parallel coefficient T. Similarly, for the P10 dataset, the recognition speed is 153,000 and 1,084,000 images per second respectively. The practical performance has increased by more than 7 times in either implementation when changing P from 1 to 8. About the conclusion of the article, we have proposed a generic design for neuromorphic computing upon one layer that allows us to construct any other sophisticated neural network. And a systematic study has been conducted on the resource utilization, performance, and accuracy of the neural network model and their dependency on the design hyperparameter. The impressive design proves the potential of reconfigurable device and episode as a flexible and powerful platform for neuromorphic computing and AI application in general. This is the end of my presentation. Thank you for listening and watching.
Hi everybody. Today I will present my paper titled Adaptive Sensor Matrix-Based Stereo Visualometry with Joy Forward Backward Translation Estimation. The content of that paper is divided 4 parts: introduction, purpose, experiment, and conclusion. In introduction, we will show some background related to our work, and we also in part 2 we will propose a linear closure form translation estimation, and some experiment result will show in the part 3 based on the evaluation on the Kitty dataset and compared to Visual 2, and part 4 we make some conclusion. I'm going to the introduction part. The SLAM means simultaneous localization and mapping. They have a lot of application to the robotic, UAV, a car, autonomous car, and have two main the component here, the localization and mapping, and the target is the minimize the error, that both error in simultaneously. And I mentioned before, SLAM component have two component is localization and mapping, and localization based on the image can code the visualometry, and the main target of visualometry is located the robot or the camera in terms of starting location, and mostly the visualometry need to estimate the transformation, the camera motion between two consecutive frames, and the feature, the target, the diagram is like so in here. The feature will be extracted from the image and matching each other, and the point beyond the feature matching will be estimate the motion. The pole estimation, there are several pole estimation, and they can divide 3 categories: 2D to 2D, 3D to 2D, 3D to 3D. The 2D to 2D is the pole estimate derived from 2D feature, and 3D to 2D is pole estimate by minimize the position error, and 3D to 2D the pole estimate derived from only 3D feature. Now I show it one popular the 3D to 2D framework is Visual 2, and the feature from this one apply for stereo visualometry, and each stereo have a left and right image, and feature in each that image will be extracted. Mostly in here is some key point, or specifically here is the people you hear bluff and the corner, and when feature extracted they will match each other and generate the 3D feature. Beyond the 3D feature in the current frame, they want project to in previous frame, then beyond the ransack the P3P approach to initial estimate the transformation and refine by minimize the revision error later to obtain the optimal transformation later. Another approach beyond the sensor matrix base, that means the 2D to 2D approach is similar. The feature extraction is similar in previous, and only here the different thing here is the rotation and translation will be estimated separately. Rotation will be estimated first, beyond the 5-point algorithm to estimate the ascensor matrix, and rotation will be extracted. And after that, the translation will be estimated with the known, with the estimate the rotation here and the 3D information provided here. With two steps, one point ransack first to initial estimate the translation and refine later by reversion error. Note that that translation refinement in the ascensor matrix by here is iterative methods, or to minimize the position error in the 3D to 3D in Visual 2 also is the iterative. And another note that the rotation estimation by 2D to 2D is more accurate than the 3D to 3D and 3D to 2D. For that reason, in here we prefer using the ascensor matrix by rotation estimation, and we propose the non-iterative translation estimation. This one we beyond the Visual 2 framework, and we change the pole estimation part. Firstly, from the feature matching here, we estimate the ascensor matrix, and after that we extract the rotation error. The estimate rotation error will be used for later for translation estimation. In here, different from the previous approach, the translation estimation we propose for forward translation and backward translation estimation here is a linear closed form. First, the ascensor matrix when we estimate from 5 points, we have, because the ascensor matrix can be dependent by rotation translation with rank E equal to, and they have 5 unknown with the unobservable scale, and from each corresponding point have the epipole constraint in like equation 1. So we need at least 5 corresponding pair to solve E. So when E obtained and rotation also obtained, and now we go into the translation estimation. Different from other approach here, we propose a closed form translation estimation. Project a 3D feature in current frame to 2D plane in the previous frame. We have this equation that in here UPVP is the 2D feature and corresponding to the 3D feature in the current frame XYZ1, and rotation RT here is the rotation matrix from left current frame to previous current frame, and S equal S here. If equals 0, that means we move from previous lap to the from the current lap to the previous lap. If S equal baseline, it move from right previous to left previous. From here we have this equation, and finally we can rewritten the equation, that equation, project equation, beyond the function of translation, like in the equation below here. They depend on the UV, the projection, 2D projection, and the 3D feature. And finally, we got this equation AX equal B. To solve this one, we need at least 1 point only, and we can use only 1 point for the success 1 point ransack to initial estimate the translation and remove outlier. The inlier after that we put to the below equation here, A1, and with endpoint we have A1 to AN, and we can solve this one to the for the refinement step. The advantage of this proposed approach is showing translation by closed form equation. Non-iterative approach like before. So the advantage here, we have two advantages for rotation estimation. We take advantage of the essential matrix base, so they have small efficient to outlier because the 5 point is minimized set for essential matrix estimation, and the mono methods for rotation estimation not affected by the imperfect calibration between left and right image stereo camera. And another thing is for translation estimation, we propose a non-iterative translation estimation. That means we can save the time. Now I'm going to the experiment result. We will evaluate our methods with other methods based on the KT dataset. That one of famous, the autonomous driving dataset, and we evaluate the 3 metric: average relative rotation error, average relative translation error, and absolute translation error. And we mostly compare to the visual tool. Is that the framework we build our methods, and the evaluation on the 11 KT session is shown in this table, and this table shows that for almost every section and over every the matrix, the backwards error is less than the visual tool, and the joy forward backward in more reduced error for both the rotation error, translation error, and the absolute translation error. And on the average, the translation error reduced from 2.4 of visual tool to 1.6 in backward, and reduced to 1.49 in the joy forward and backward approach. And here I show the one detailed example for section 0, and here you can see that the error of the joy forward backward in black is close to the ground truth than the backward in blue and visual tool in green. In similar like the section 02 is similar manner. And we also estimate the rotation and translation error in terms of travel distance. And in the below is the first one, a rotation error. The backward approach and joy forward backward translation estimation is lower than the rotation of the visual tool, and similarly the joy forward backward approach also slower than the backward in the translation error, and error will be reduced when travel distance is increased, but for visual tool its translation is increased when the travel distance increase. In here we can make some conclusion that in here we introduce essential matrix by visual odometry, and we also propose a nonlinear iterative translation estimation, and the result show that the forward backward translation estimation achieve 4% enhancement to backward translation estimation, and the forward approach translation approach achieve 1.6%, and with with joy forward and backward obtain 1.49% in terms of translation estimation respectively. So thank you for listening. If you have any question, please let me know by email. Thank you so much.
Hello everybody, my name is Trần Công Thìn from the Institute of Electronics, the Military Institute of Science and Technology, Vietnam. Today, I would like to share a part of our study results with you about the gun shooting localization. Now, I'm going to talk about my research paper, a modified localization technique for pinpointing a gunshot event using acoustic signals, presented for INSCOM 2020. Now, let's have a look at the content in my presentation. I have divided my presentation into 4 main parts. First, the introduction and motivation. The second is localization methodology. The third one is methodology evaluation and the conclusion. Now I will show them sequentially. Now let's move to first part. As we have known that firearm violent crime frequently happens nowadays. However, criminals may not arrested immediately because such shooting incidents are not located quickly enough. Therefore, an automatic method of gunshot localization is very helpful for chasing and catching criminals. A firing gun usually emits acoustic muzzle blast waves propagating spherically outwards with a speed of sound in the air, as you can see on the figure 1, which shows firing a gun and a resulting acoustic signal. So, such a signal can be utilized to localize gunshots. There are 2 main localization approaches, which are energy-based and time differences of arrival-based or TDOA-based. Although the energy-based localization technique can bring about high localization accuracy, it is challenging to have a real wave energy propagation model. In contrast, the TDOA-based method is extremely simple because it can localize a sound source without a complex propagation model. Therefore, our proposed method is a modified TDOA-based technique for localizing a gunshot event using acoustic signals. Next, I will present the localization methodology in my paper. The overall diagram of proposed gunshot localization is shown in the figure 2. There are 2 phases: event detection and source localization. First, I will talk about the event detection. As we can see that on the figure 3, it exhibits a typical gunshot event in an acoustic signal emitted by firing a gun. To detect this event, we exploit the Neyman-Pearson theorem to determine the threshold, which is shown by red dashed lines in the figure 3. Such a threshold is calculated by using equation 1. After we have a threshold, we will compare signal samples with the threshold, and all the samples exceeding the threshold can be the candidates belonging to gunshot events. Next, we will group the candidate samples into events and filter unsatisfied events out relying on equation 2. The total event detection process is carried out by the diagram shown in the figure 4. The output of the diagram is gunshot events in a signal. Okay, after the first step, based on the detected gunshot events, we will localize their emission source. We arrange 4 sensor nodes on the rectangular working area M1 to M4 with the size of 500 meters. The coordinate system OXY is established by the rectangle X and vertex as shown in the figure 5a. Each node is comprised of 3 acoustic sensors M, I, J, in which I from 1 to 4 and J from 1 to 3, and they are equivalently arranged around a circle with the center Mi and radius of R equal to 5 cm, as shown in the figure 5b. After setting up the model, we are going to estimate the shock location. As seen on the screen, the figure 6 shows the gunshot location estimation. The key step of estimation is to determine emission directions M1H1 to M4H4. Afterwards, we determine crossing points S1, S2, S3, and S4. Finally, the source location SE is the quadrilateral center of 4 points S1, S2, S3, and S4, given by equation 3. To determine the emission direction, we will use the diagram as shown in figure 7, which is for a 3 sensor node. The first block of the diagram is event grouping. The figure 8 shows grouped events from 3 signals acquired by 3 sensors M11, M12, and M13. The event grouping constraint is given by equation 4. That is a criterion for finding neighboring individual events from different sensor channels. After we have grouped signals, we will determine TDOA of them, because we fixed sensor places, so we can establish a prior source coordinate map using a specific sound speed of sound propagation in the air. And finally, we will use a minimum mean square error estimator to search for the signal emission direction. Next, the construction source coordinate map is shown in the figure 9. We divided the working area from M1 to M4 into shells with the size of delta D and delta H. Each vertex HK of XK and YK gives us a set of TDOA using equation 5. From TDOA of detected grouped events and the prior source coordinate map, we can find out a satisfactory HI of HI and YI using equation 6. And lastly, we will obtain the emission direction MI HI. Hence, the source location can be estimated. Now, to evaluate the proposed gunshot localization methodology, we initially recorded signals emitted by 10 real gunshots using only one nearby sensor as shown in figure 10. Next, we simulate a signal acquired by a sensor by using the model as presented in equation 7. This is based on the sound wave propagation and attenuation in the air. There are real 10 gunshots. Accordingly, we will have 10 events in a signal acquired by the X sensor of 12 installed sensors. Each of them shows a distinct signal because they are arranged at different positions. Hence, our model can provide nearly real signals to evaluate the proposed model. Now, let's move to the final evaluation step. We simulate 4 gunshot source locations from P1 to P4. The figure 12 illustrated the estimated location corresponding to simulated gunshot locations using our model and proposed localization method. Next, we implement and compare for well-known mechanisms for determining TDOA. The first one is crossing a threshold and signal, CRS. The second one, position of maximum amplitude, PAK, or our methods. The third one is AK's information criterion, AIC. And the last one, cross correlation function, CCR. And then we compute average of distance difference of the 10 gunshots and estimated locations using equation 8. As seen in the table 1 and table 2, we can see that the resulting errors without noise on the methods show nearly similar errors. However, if with noise adding, the CRS method is strongly influenced, while the others return acceptable results. In terms of computation, our method PAK is the most appropriate because our method is carried out by simple computations and its error is relatively small, even in the noise adding case. So far, our proposed method, which is a modified method localizing a gunshot event based on TDOA introduced in the paper, can be summarized as follows. Using 12 acoustic sensors arranged in 4 nodes, each of them comprises 3 sensors. Sound events are detected in individual signals of nodes through a false alarm probability. Direction of a gunshot event is found with the assistance of MMSE using the time differences of arrival between acoustic signals acquired by sensors of a node. The sound source location is the center of tetrahedron, which is created by 4 crossing points of 4 pairs of adjacent emission directions from sensor nodes to the sound event. To evaluate the proposed method, we created signals from a signal containing 10 real gunshot events using a sound wave propagation model in the air for a working area with the size 500 square meters. Comparing various methods determining the time differences of arrival, the maximum amplitude-based method is the most appropriate. With the results, the location errors are 7.1 meters with 1.4% and 7.4 meters with 1.5% for noise, absence and noise adding respectively. We have completed our presentation of a modified method localizing a gunshot event based on the time differences of arrival of acoustic signals. Thank you for listening. If someone have a question, please feel free to email me. Once again, thank you very much.
Hello everybody. Today I would like to present our paper named Table Structure Recognition in Scan Image using a clustering method. The presentation includes the following session. First, we introduce problem that we face in the OCR processing of scan invoice. Next, we present some recent work to tackle the problem. We then propose our method called clustering, which is based mainly on clustering method to recognize the table structure in invoice image. And next, we show our experiment result on three data sets. Finally, we conclude our work. As you may know that in the OCR processing of scan invoice image, we face a challenging problem, that is table structure recognition. This is really challenging due to the fact that the invoice layout is very diverse. Second is that there are a lot of information field, and the data table may be very large. And finally, the quality of the scan image may be not high enough for processing. And the table structure recognition is a very difficult task because if we can recognize table structure, then the cell OCR processing would be much easier. Recently, there are a lot of methods which was proposed to solve this problem. We sit here, two of them. The first one is the SRT, which is proposed in 2017. The method is semantic segmentation.
downsampling and upsampling the image to detect the column. And then they use a single shot multi-box detector to detect row using a dataset ICDA 2013, which contains 34 document image. They achieve an F1 score of 91%. However, by this method, the empty cell in the invoice image cannot be recognized. Secondly, in 2019, a method called tablet proposed by Paliwa and this method also using semantic segmentation to detect column, and the row detection is based on the horizontal line rule of words, and the words are recognized by test right OCR. They tested the method also in ICDA 2013 dataset and achieved a similar F1 score of 91.51%. Once more, the sparing row cannot be recognized by this method. Different from the previous method, which based mainly on the deep learning network. In this paper, we propose a method that is based on a clustering method. Our method called clustering, which includes the following steps. First, we remove the noise from the image using a clustering method called dbScan, and then we use a graph text detector to detect all the text, especially all the character in the invoice image. From the text field of all the character in the invoice image, we can detect all the row and all the column and then we reconstruct the cell for the table structure. Firstly, to remove the noise, we use dbScan. In this case, dbScan we use two parameters of dbScan. The first one is epsilon, which is chosen as 1 pixel, and the mean symbol is chosen as a character it is a smallest number of pixels of character in of the language, and we find that we can separate all the character and the noise, and from that we can exclude noise from the image. To detect the text, all the character in the invoice image, we use a graph, which is the best among current detection methods. The graph is fitting with magnifier and bounding box parameter. Based on the text detected so far, we propose horizontal clustering algorithms to detect the row. Here we propose three algorithms: horizontal clustering algorithm, median high calculation algorithm, and probing algorithm for horizontal clustering. The horizontal clustering algorithm is as follows. We assign n as the total number of character bounding box detected by graph, and we assign mean sample of parameter BB scan is the number of pixels of the symbolic character in the specific language, and we also assign epsilon at the variable to be fine-tuned. So this algorithm aims to find out the exact value of epsilon. In the probing algorithm for horizontal clustering, we change the value of epsilon following the median high of the character. In fact, epsilon is changing from epsilon to k multiplied by epsilon, where k is ranging from 0 to 1, and epsilon is started at the value of median high. The output of the horizontal clustering algorithm, meaning the DB scan algorithm, is the number of cluster, meaning that's the number of row in the invoice image. By changing epsilon, we produce a larger value of number of rows, and from that we can draw a graph of density of the number of rows while changing the value of epsilon. The graph shows us two peaks. The first peak represents the number of natural. Here is 33, and the second peak represents the number of smaller rows. Here mean 46, and this indicates that one row includes two smaller rows. To detect column, we use a similar algorithm as to detect row. This called vertical clustering algorithm. In this case, we also fix the mean sample of the mean sample parameter of the DB scan algorithm as the number of rows found in the previous step, and then we also fine-tune the epsilon parameter. Epsilon is fine-tuned from epsilon min to epsilon max. In our case, we choose epsilon min is equal to 1 and epsilon max is equal to 200. Each step epsilon is increased by 1. and the number cluster founded by DB-scan indicates the number of columns in the invoice image. And we draw a graph representing the number of columns according to the value of epsilon. And we found that the knee point of this graph represents the exact number of columns in the invoice image. After detecting rows and detecting columns of the table image, we can reconstruct the cell of the table image by calculating the median height and the median width of all the character bounding box found so far. We have experimented our method on 3 datasets. The first is collected from the internet, which contains 397 scan images. The second one is ICIDA 2013, and the third one is ICIDA 2019. From the experimentation, we found that on the 397 scan image, the F1 score of our method is 87.5%, and on the ICIDA 2013, the F1 score is 98.5%, and on ICIDA 2019, the F1 score is 94.5%. We also compare our accuracy, our efficiency with the SRT and tablet presented so far, and we found that our method outperformed both previous methods. Here it is 98.48% compared to 91.51 and 91.44%. For conclude our work, table structure recognition is an important task in OCR processing for scan invoice image. In this paper, we propose classicity method based on DB-scan clustering algorithm for table structure recognition. On the 34 test image of ICIDA 2013 competition dataset, the method outperformed the SRT and tablet with a significant higher F1 score that demonstrated the efficiency of our method. However, classicity bears certain inconveniences, especially for complicated table structure where it is spread in row or column. This is also our future work. Thank you so much for your attention.
Hello, I'm Guy. Now I will present our research about distributed watermarking for cross domain of semantic image database. I would like to introduce Our research team, including me, Mr. Kim Thang, and my instructor as Associate Professor Dr. and Dr. Downlink. Welcome. We come from Liquidon Technology Technical University. And we know this is the watermarking is technique embeds the secret information into the digital content without degradation. The embedded content, also called cover content, can be used to distribute to the users who browse the content. When dispute happens, the embedded information secret is needed to extract from the embedded content to verify the copyright of the related parties. In this study, we focus on the proposal a new method of distributed watermarking for cross-domain DCT FPD for semantic large image database. Also, we compare proposed method with DWT-based method about invisibility and robustness. In summary, briefly introduce our contribution as follows. The first, we propose a new distributed watermarking methods for semantic image sets extracted from dataset published for deep learning application. The semantic image set is defined as a set of images belonging on class from deep learning dataset. In case of video format, the semantic image can be defined as a set of frames from a short video. This is the first consideration of copyright protection for deep learning published datasets. The second, we have an idea to distribute the separate shadow over own image set to keep the security of original watermark. Only the owner have the secret key can extract the original watermark to prove the ownership of datasets. Finally, we try to apply the proposed method on the short video file in order to verify the efficiency of solution. Short detection process can be simplified performance by using some conventional methods on frame from on shot and uses to embed on scramble shadow in order to improve the security. In this slide, I will give the definition of semantic large image database. Semantic large image database as a set of image belonging on class of one object. In case of video file, the semantic large image dataset can be defined as a set of frames from one shot. For instance, as the explanation of casual cipher 10 is an established computer vision dataset used for object recognition. It is a subnet of the 80 million tiny image dataset and consists of 60,000 color image size 32 x 32, containing on a 10 object class with 6,000 images per class. In this algorithm, construction will generate and shadow watermark SE from all the original watermark W, and revealing process will reveal original watermark W from shadows. Our main purpose focus on the four sub-processes. First, shadow construction process. Second, video embedding method. Third, video extraction method. And finally, watermark revealing process. The first shadow construction process. The shadow SE can be seen in figure above. All shadows are randomized based on the stress key, then for only the owner who keeps the key can reveal the watermark information. This figure shows video embedding process. Video embedding process has detailed following. The density transform is used for the first time to retrieve the low frequency region for embedded information. The second time density to apply to block. Apply to block use like is block form multiform to create magic A for embedding information. Every transform is used with four multiform block of magic A. Use the largest element of every singular value to embed information. The process of embedding information of this is performed on 3 color channel RGB. This is equal to embed. The figure below show videos extraction process. To extraction the watermark information from a watermarking broadcast video with that. We do not need the original video V. The secret key KI and number of shadow and are required. The process of video extraction shown in video below. This slide shows detailed video extraction process in contrast to the embedding process. In the extraction process, also use 2 density transform. 2 times. This slide shows details the video extraction process in contrast to the embedding process. In the extraction process, also used two-time density transform and one-time FPD transform. Extraction the information in equal 10, then use routing techniques in equal 11 to select the best data. And the finally, watermark revealing process to obtain the watermark from extraction shadow using revealing in unrolling arms. Use in force. To test experience test and data environment implemented in Python version. Python video data container format with 300 frame scale and same size 1020 multi-trend 1020. Watermark binary image size 32 multi-32. In order to generate the shadow watermark at I0, apply the for sequential scheme and equal 4. Function random in and set 1 to 0 to generate sequence ki. The embedding chain factor Q equal 15 and the threshold T equal to. Compare our global method with density needability display. Measurements to evaluate the imperceptibility of watermark's video. The big signal to noise ratio (BNR) is adopted. Mean square to evaluate the robustness of extraction methods using NC-NOMA normalized correlation. With robustness measure if the value of NC is close to 1, this means that the robustness is better. Normally, the NC value is acceptable if it is 0.55 or higher. This slide shows experimental result. In this figure, show on PNR value of on frame from 3-step video were calculated and compared on PNR value obtained between our robust method and readability by methods. The average PNR value from serial on-frame are shown in figure 6. Based on our experimental result, our proposed method achieve better results than that of DWT by method. Next, this figure 7 shows the visualized quality of on-frame from set video. We extracted the first frame from frame and compute PNR value from the sub-result as given in this video. It is clear that our result is better than the result of DWT based methods. To test robustness, the result of extractions watermark are given in figure can be seen. The performance of the proposed algorithm under filtering stage is better than this WT by method. The next figure, the result extracted watermark are shown in figure above can be seen. Both methods are not robust against shown and vapor attack. However, there are robust against noise attack. Next slide. The result of our experiments are shown in the figure above. As can be seen from this figure, our proposed method can extract exactly the watermark information. On the other hand, DWT by method is not robust against strong killing attack. The figure shows that both methods robustness against JPEG compression. Based on the result, we can conclude that our proposed method and DWT based method are acceptable for JPEG compression. Conclusion: we have a method to distribute original watermarking to generate scramble shadows and embed structural shadow into the scratch frame. The setup frame from shot. We embed the watermark information into FPD domain. It is robust against some attacks such as median blur, Gaussian noise, shown and vapor noise attack, JPEG compression, and geometric attacks. Compared with other related work, proposed method watermarking method perform better in terms of invisibility and robustness. Our proposed watermarking method algorithm can be extracted for audio signal processing or distributed database. This result is finally this result is funded by Vietnam National Foundation for Science and Technology Development, fostered under number 102/01/2019. Thank you for listening.
Morning, everyone. I'm Van Hatang from the Faculty of Information Technology, Leguidon Technical University, Hanoi, Vietnam. On behalf of my colleagues, it's my pleasure to present our paper entitled Depth Image Reconstruction Using Low Range and Total Variation Representations. So the outline of our talk has 5 main parts. First, we read some introduction about depth imaging. Next, we present a model for depth spark imaging, and we will present our proposed method based on low range and total variation depth reconstruction, following by some experimental results and conclusion. So depth imaging and sensing technology has been made a wide impact and had a wide range application in computer vision, such that it can be applied to autonomous driving and robots navigation, and in the application such as action recognition and augmented reality. 3D cameras such as Google Tango, Intel Realsyn, and Microsoft Kinect have been developed for 3D imaging or depth imaging. Here you can see an example of a depth image of an indoor scene where we can have both RGB image on the left hand side and also the depth image that will contain the information from the camera to the optical surrounding. This image has been captured from New York University depth dataset. So the challenges in depth imaging include missing data or pixel due to human vision, fast sensing when we want to capture only a far reduced number of measurements, or poor hardware performance. And among those, we can see here an example, an indoor scene, and on the left panel, here is two scene, and on the right panel, we can see there are a lot of data or pixel on the image capture had been missing, and this missing have very negative effect on target detection and localization after processing. So the objective of this study is to enable fast sensing and also to reconstruct the missing pixel or reconstruct the depth image from far reduced number of data we obtain. And towards this aim, we propose an efficient convolutional method for depth image reconstruction. Now, we come to the depth by imaging model. Let's consider a depth sensing model and assume that we obtain only y. Y is a vector containing only n pixel we obtain, and we aim to reconstruct an unknown image z of m pixel. And the relation between the observed data and the unknown image we want to reconstruct is in equation 1, that is y equal to c and z. Here c is a sampling matrix of size and time. Given the corrupted image y, or the data we observe y, and the sensing matrix phi, I wanted to reconstruct a full and high quality depth image z. That is a linear equation 1. To do so, existing method or sparse representation of roads, they try to sparse representation of image Z by equation 2 here perceived is a dictionary for sparse representation, as the most common view is a weighted basis. And in the equation, I see a vector of coefficient that is a sparse vector, which means I have only add non-zero component by the L0 norm at equal to 0 norm I. And because the L0 norm is NP-hard problem, and so in implementation, the counterpart L1 norm is often used to regularize the sparsity because it's a convex one and it's easier to solve compared with the L1 norm problem. Now, from equation 1 and 2, we can obtain the coefficient by solving a minimization problem in equation 3. Here we have two terms. The first term is a least square term, and the second one is L1. And this problem can be called L1 regularized least square minimization problem. And here lambda is the regularization parameter. Since PC is orthogonal, so after we obtain H, we can obtain the image Z by multiplication with PC. And also we also have problem 3 and problem 4 by replace the variable H by variable Z. And by doing so, we can obtain directly the image by minimizing the problem in equation 4. In this paper, instead of only using the sparse regular like L1 norm, we introduce another two regularization. It's called low rank. Here we stand by LR and total variation STV regularizer. We introduce into the model to strengthen and to stabilize the depth imaging model. So by integrating the two regularizer into the model 4, we have model 5. Here we have the nuclear norm imposed on the image set. The nuclear norm is can be defined by the sum of the singular value of submatrix sets. And because the low rank is regarded as a non-local or global realizer, and it considers only the global information of the image. To take into account the local information, we use a local TV regularizer to guarantee the local spatial consistency. So we come to the problem stage. Here, another regularizer is TV is imposed on that. Now our task is to solve problem stage, and we will obtain the depth image set. We propose in this paper an algorithm based on ADMM. It stands for Alternative Direction Method of Multiplier Techniques. This technique is very powerful technique that allow entire minimization problem to be decomposed into sub-problems that can be handled more efficiently. By doing so, applied to solve problem 6, we introduce 4 auxiliary variables, and it had been detailed in the paper. And in particular, we introduce S, R, T, and U. And by doing so, we can cast minimization problem in search into the constraint problem in 7. And 7 is much easier to solve than the problem 6. For more detail on the IDMM methods, people are recommended to refer to the references here. Alternating direction method of multiplier, and also distributed optimization as learning by alternating direction method of multiplier. So the detail of the algorithm had been presented in the paper, and here the algorithm. And this algorithm start by initialization of the variable and iteratively updates the variable until conversion. Here we can regard the algorithm stop when the related change of the image is very small or negligible. And here it's very important to note that the algorithm is computational efficiently because the variable update have a closed form solution with element-wise computation. Now we turn to some experimental results. We use datasets obtained from mid-library stereo datasets, and here is very benchmark public datasets, which ground truth data, and we use PFNR at a performance accuracy computed at equation 8. So the higher PFNR, the more accuracy of the reconstruction. First, we evaluate the performance of the low-rank total variation model we propose in this paper. We see that image of an art with size 277 times 345 pixels. And as a first experiment, we keep only 50% of the data. That means only 50% of the measurement are used to reconstruct the depth image. And here's the result. In figure A, here is the ground truth image of an art, the depth image. And B is a mask. The mask that is the mask is B. We use to select the measurement. And because only 50% of data are kept, we can see that in figure C, the depth image we obtain is corrupted, which PFNR only 7.08 dB. And now we use a proper method to reconstruct the depth image. As a result obtained, we present in figure D. Here we can see that in visual quality, figure D and figure A is almost the same. And the quality of the reconstructed image by the low-rank TV model here is obtained 31.28 dB. It's very promising result. And here, to go deep into the reconstruction process, we record the PFNR chain, during the reconstruction. And here's the iteration of the algorithm. And here is a PFNR of the image obtained. And we also reconstructed the chain of the relative chain of the image obtained during the minimization. Here we can see that during the optimization, the quality in terms of PFNRs improved. It seems to be after 60 iterations, the chain is not marked. change normal, and it obtained more than 30 dB. And in terms of relative change of, or conversion of the algorithm, we can see the algorithm tend to converge after 80 iteration. And here we stop when the algorithm reach 116 iteration, and at this point the relative change reach a total of 9.5 times 10 minus 5, very small. And we also compare the proposed method with other imaging approaches. We consider two other imaging models, that is sparsity only by methods for depth reconstruction in the reference file here, and also the sparsity and TV realization in the study stage. And we also evaluate those methods in two missing scenarios, random missing and large column missing. And here's the result. Figure A shows the gratitude of a chair image, the depth image of a chair, and figure B shows the corrupted image which missing data pattern, and figure B and figure C is a large column missing, and figure D shows the reconstructed image obtained by the SPA model. We can see that it's not good result because there are a lot of missing patterns. And figure E shows the reconstruction of the SPA and TV. And figure F shows the result for the proposed methods. We can see the proposed methods can obtain very good result compared with the two other one. And figure Z shows the image reconstructed by the SPA only for the large column missing. This method cannot recover the missing data well. In contrast, our method can handle this missing pattern very well. The result obtained so in figure H. So here in the table, we can see the performance comparison in terms of P antenna. So in both cases, the proposed low range and total variation can obtain a very good result for both random missing and large missing. So in conclusion, this paper presented a new low range and total variation imaging model for depth image reconstruction from incomplete data measurement, and we formulate the start of depth image estimation at a joint low range and TV regular line minimization problem, and we propose an algorithm based on ADMM to solve this problem, obtain the image. And after some experiments on the benchmark dataset, we can see that the Pro model can see a high quality image for different missing data cases, and it enhances the quality of image reconstruction and outperform other state-of-the-art in terms of P at NR. Finally, thank you for your attention.
Hello everyone, I am Minh Hiểu Nguyễn, student at Hanoi University of Science and Technology. Today I will present about my research, deep learning-based hyperspectral image analysis for stream contaminated detection. My presentation have 5 sections: motivation, related work, system model, experiment and research, and conclusion. As we all know, shrimp is nutritious food. However, many inchine lines of shrimp are refused every year because shrimp are pumped impurity, and the most injected impurity is agar. Therefore, before being exported, shrimp containers are always inspected by X-ray methods. Testing by this method has some harmful effects, such as after checking by X-ray method, shrimp cannot be used. So we will build a system which can detect contaminated shrimp using hyperspectral image. Hyperspectral image is imaging that uses hundreds bands across the electromagnetic spectrum from infrared to the end of visible spectrum. So hyperspectral image can be applied in astronomy, agriculture, biomedical imaging, geoscience, and so on. Hyperspectral image is taken by special camera. In sync research, we use SPECSIM F10 camera which can take a hyperspectral image with 224 spectrums. Because hyperspectral image contains more information than red, green, blue image, there are many food classification research with using hyperspectral image and machine learning algorithms such as using subvector machine and hyperspectroscopy to evaluate the fruit and vegetable quality. The hyperspectral image of the fresh and stale shrimp were classified by logistic regression algorithm and classified into fresh and frozen meat by hyperspectral image and convolutional neural network algorithm. And here is the result of the research. I will talk about our system. Our system have a 3 blocks: marking and denoising, data injection, classification. Hyperspectral image of shrimp is removed background and noise by masking and denoising. After that, data of body shrimp is extracted by sliding window. Finally, the data of body shrimp is classified using neural network algorithm. Marking and denoising block. First, we take 4-point spectral, includes 2 lines, 1 shadow, and 1 body. Like we see here, the spectrum of shrimp body is different from spectrum of line and shadow. So this noise data should be removed to train the best classification model. To eliminate the background and line noise, marking algorithm using line intensity is used. Red, green, blue image is converted to SV image and grayscale image. Grayscale image is converted into black and white image by also threshold. Then histogram diagram is calculated by SV and black and white image. Finally, using histogram and SV image, we find the mask. However, this mask cannot remove shrimp layer and the shadow, so we're using label me, a website label for computer vision task to draw contour of body shrimp, and then we have the last map, which is combined light intensity segment and shrimp body contour. After removing light, noise, and background, data is extracted by sliding window method. The shrimp body is divided into a grid size 8 times pixel. Hyperspectral data of shrimp body is average from the hyperspectral curve of every pixel in S times S window. Rejecting data, we have a spectrum of contaminated stream and clean stream. Like we see here, contaminated stream spectrum red curve and clean stream blue curve are mixed. So we apply TSNE of machine learning algorithm for visualization. This algorithm is a nonlinear dimensionality reduction technique for embedding high-dimensional data for visualize in a low-dimensional space of 3 dimensions. Like we see here, TSNE output of contaminated stream and clean stream is distinguishable. So we can confirm that our data can be able to apply machine learning algorithm to classify contaminated stream. In classification log, deep neural network is used to detect contaminated stream. Our model have a 4 layers include input layer, 2 hidden layer, and output layer. The input layer has 224 units corresponding to 224 wavelengths of our hyperspectral image. The output layer has 1 unit. As a result is binary classification. At each hidden layer, there are 256 units and using ReLU activation function. In our research, our dataset is divided into 3 sets: training set, 60% validating set, 20%, and testing set, 20%. Training set is the input of deep neural network for learning, for estimating the parameter. Validating set is used to turn deep neural network model hyperparameter, and testing set is used to evaluate the model. To evaluating our model, we use accuracy and MO score. Instead, accuracy is calculated by the sum of correct prediction divided by own prediction, and MO score is calculated by double of precision multiply recon divided by sum of precision and recon. After training model with other grid size 1 times 1 pixel, 3 times 3 pixel, 5 times 5 pixel, and 8 times 8 pixel, we have the result like here. The data point of window size 5 times 5 provided the best result. The accuracy is about 98.11% and MO score is about 94.29%. This may be true because averaging of spectral in each window may be like averaging filter, which can reject several types of noise such as sandpaper noise. However, averaging over large size of window like times 8 pixels may lose many features. And this is the result in the stream. Here we can see the result in contaminated stream with 5 ml agar, 4 ml agar, 2 1 ml agar, and clean stream. So our result is not only detect exactly contaminated stream but also can identify which part of the body contain impurity. Summary: this result demonstrates the ability to classify contaminated stream by hyperspectral image and deep neural network. And in this result, stream classification requires only few hyperspectral images. And in the future, maybe there are many food classification problems can solve by applying hyperspectral image and deep neural network. Thank you very much for watching and hope you enjoy my presentation.